And the second partner is a Technology Partners Foundation, is one of the leading European, actually, industrial and research organizations. What are we doing here now? I'm sure you know, but just to remind you, that's the first meeting, just to, I hope, to inspire you to some ideas. What do you want to do with your companies, with your businesses? So please, if you have any ideas, if you have any questions, any fields you want to share with us, to point the field of interest for you, what is interesting, especially particularly for your businesses, for your companies, please let us know. There is a chat box, so you can type it there. There will be also evaluation forms. You've probably seen that, or you will see it. So there is a special spot for that, just for pointing out what do you want to learn about. That information from you will help us to prepare tailor-made workshops and courses, training in the future with local experts. We will prepare it in a few months, as you probably know. So please, anytime you want, just type whatever you find interesting in chat box. If anything is unclear here during the presentation, also please let me know. You might just raise your hand or just unmute your microphone and speak up. We'll try to talk about it. Okay, so just to present the structure of the webinar, it will be divided in 3 parts, actually 3 presentations just for technical reasons. We will have a break, a small break, like 3-5 minutes long after the first part. Then we go to the second and third part. So the first part, we'll present some basics of remote sensing. After that, we'll go to some important properties of satellite imagery. After that, to radar remote sensing, which is very interesting, and to other types of remote sensing data. That's the plan for this first part we'll have now before the break. So first thing, I don't know what's your basics actually, but what is remote sensing? Of course, that's getting information about objects from distance, especially from aircrafts or satellites. So that's it. Actually, that's remote sensing. So we get information about Earth's surface. But why remote sensing is useful? Why do we find it important? The first thing is that we can get the bigger picture. Of course, like from a satellite level, from a few hundred kilometers, we can get a really big picture. It means big picture, like thousands or hundreds of thousands square kilometers at once, in a moment, instantly. So that's the first thing. So this is one thing. And the second one, we can see more, not only like the bigger area, the bigger picture actually, but we can see like the information we can get is more profound, is deeper. We'll talk about it, of course, in a few minutes. And actually, it's a quite, well, relatively actually cheap source of data. Of course, to get the satellite to the orbit like costs millions of dollars, but after that, it's quite cheap. And actually, we can download some of the data for free, and even it's not free, we can find some quite cheap data useful for us. So the first question, how is that we can see actually more? There we have, I don't know if I can, because there is this bar. I see all of you. Okay, I can hide it. Yes, I can. Great. So there is a electromagnetic spectrum, like just a schematic of that, and we can see that there is just a thin, very thin line of visible spectrum. This is what we can see with our eyes. That's a very small part of the spectrum. There are a lot of different, bands of electromagnetic radiation, and they might be very useful. We cannot see it with our eyes, but we can build some tools to see it for us, actually, to get this information for us. And this is how we can get more information, like scanning, taking pictures in different bands of the spectrum. So this is why we can see more. Actually, we will see it in few minutes. How does it work actually? Let's start with this range because there are a lot of bands, a lot of ranges. So we'll start with optical range. Optical range means like typical images we all know, like taking picture with a camera in a smartphone or whatever, but also some part of infrared radiation. So this first part we will focus on for now. Yeah, the problem is that we have the experience with this visible spectrum, of course, but we don't have experience with this infrared. So how is that we know what we see when we see the images? Okay, we can get image like in infrared band, great, but how can we know that you know what does it mean that it's bright or it's dark? What does it actually mean? So for that we learn something called spectral characteristics. There are like functions. They show the relations between different radiation bands. Like here we can see like visible bands, blue, green, and red, and near infrared, middle infrared. So this is this visible part. So they relate those bands with reflectance for different types of objects. So how can you read it? We have this different colors here. For example, let's focus on this green one. That's the vegetation. That means that here in this visible band, in this visible part of the spectrum, we can see it as green because it reflects more of green than blue and red. So that is why we can see the vegetation as green. But what we can see actually with our eyes is that it's very, very bright, extremely bright in near infrared band. We cannot see it, but we can take a picture actually in this band, but using some tools, of course. So also we can see, for example, that this near infrared might be very, very interesting because also we draw those spectral characteristics not only for different objects, but also for different conditions of objects, for objects of different conditions. Like here we have this yellow line of vegetation as well, but dry vegetation. So dry vegetation has different properties, different characteristics than green, healthy vegetation. We can see here drawn with this green line. So we'll discuss it, of course. To make this gathering, this collecting of information easier and more, well, easier to interpret, easier to process, we take those images in the manner of so-called multispectral imaging. That means that we take independently different images in different spectral bands. Like here we have blue band. Of course, it's not blue. Actually, we can see that it's gray. But blue band, it means that it gathered the information. It registered only blue radiation, only those parts here written, drawn here in this diagram. So it means that only this part of this radiation was registered. So whatever is bright here in this image, it means that it reflected more of the blue band. And when we can see, of course, green band as well, we can see that it's different. So they are taken independently, of course, in the same moment, in the same instant, actually, but they show us different characteristics of those objects. Red one, again, something different. And when we switch to near infrared, which we cannot see with our eyes, we can see that the difference between like red and near infrared is really, really, really significant. So this is how we can, let's say, translate this information, this data from this band we cannot see with our eyes to, you know, to actually understand it. So, for example, when we look at this spectral characteristics, we can see that vegetation reflects very much of this band, of this radiation. So whatever is bright here, it is probably it is probably a vegetation. And we can switch again to red. And if it's dark here, it's probably vegetation, because we can see that it's very low here. So it reflects the vegetation, reflects very little of this spectral band. So yeah, so that's how we can interpret those images. And another one, like middle infrared or short wavelength infrared, it has different characteristics. It tells us about different properties of objects. So actually, every single band tells us something more, something different. So the information from the different bands is actually complementary. So this is how we can use it and how we can interpret what is actually taken in the picture, in the image. To visualize those images, we rarely use those single bands as we saw before. Usually we create something called color compositions. Like here we have something called natural color composition or true color composition. It means that we get those three visible bands, blue, green, and red, and we put them through three different appropriate like filters, basic or true color filters. We always create those images from blue, green, and red component, but we can put through those filters, through those components, different bands. So when we put blue through blue, green band through green filter, and red band through red filter, we create something called natural or true color composition, which means that the colors here are true. The colors here are just like we see them with our eyes. So it's quite easy to understand. It's quite easy to interpret. For example, we can see that, okay, so here is something, we can see some road, we can see some build-up area probably here, some forest there probably, etc., etc. We can see that it's vegetation because it's green, etc., etc. So this is one way to present this information. But also we can use those different spectral bands, which are actually more informative than visible bands. So for example, near infrared, we can put it, well, we don't have any, like infrared color, so we have to choose from those three basic colors. So we decided here to put near infrared through this red filter. So it means that whatever is bright in near infrared, whatever reflects a lot of this radiation, this part of radiation, it will be red in this image, because we translate it as red. Let's say it like that. So we put red through green and green through blue, and then we have something called false color composition. Of course, the colors are false; they are not true anymore. So we can call it false color or infrared color or color infrared composition. And it's completely different, of course. And it's, well, actually, when we don't have experience, it might be at the beginning more difficult to understand, more difficult to interpret, but actually it's much more informative. And it's even better when we add another infrared. Like here, we put short wavelength infrared, or this middle infrared here, through this green filter, and we can see how much of the colors, how many colors we can see there. Let's compare it with this true color composition. It's much better here. Every color actually shows us that this particular object is a bit different than the other objects of different color. We cannot see it here, because we can see it here. So this color composition, this information, this data is much more informative than this visible data. So this is how we can see more. We can see something more than we can see with our eyes. Okay. Of course, that's not that doesn't affect only, that doesn't touch only optical imagery. There will be also radar and thermal imagery, also laser scanning. So we'll talk about it a bit later. But now let's focus on different properties of imagery. Not only optical actually, but mostly that refers to optical imagery. So we have different properties. We have to take into account when it comes to like deciding what data we need, what data we'd like to use for our purposes. So let's go to the first one. Probably like the first thing we think about when we think about images, satellite images, it's a spatial resolution. That means how detailed image we can get with this data. Basically, it's a size of the smallest object we can see in this image. So that's the spatial resolution. And just to point it, very like firmly, that's not a pixel size. They are related. They are strongly related, like linearly related, but that's not the same thing. When you think, for example, that you need an image when you can see for sure 1 meter size object, you don't choose 1 meter pixel size. Unfortunately, usually we don't have this thing, this size of the smallest object written down in some technical, files. You won't find it. We will find always pixel size or something called GSD, which is actually the same, ground sample distance. But actually, it's like to get the information about 1 meter size object, you have to have like 3 times smaller pixel. So for 1 meter, you have to have 0.3 meter pixel size. That works this way. We don't have a time to go into details, unfortunately. But if you have any questions, you are interested in this topic, please let me know, and I will be happy to guide you to show you some sources or even correspond or something. So that's of course that refers to every topic we will talk today. So they are related, and this is how it works. So depending on the pixel size, we can see smaller or bigger objects in the image, but it's not actually the same thing. So just to like swipe through different images of different spatial resolution. This is actually an airborne image, but we have VHR, which stands for very high resolution satellite imagery, which is even better than this image. We have this 0.3 images, for example. They are quite expensive actually, but we can buy it anyway. So we can see, I don't know, shrubs, maybe bigger rocks or something like that. So we can see a texture of the forest. That's very detailed. This is 1 meter. This is 2.5, 5 meters. So we missed a lot of information, of course. That's normal. Then 10 meters, that's, for example, the spatial resolution, this pixel size of Sentinel-2, which is quite an important, we'll talk about it later, quite an important satellite for us. 15 meters, 30 meters, or even 80 meters. We have, of course, satellites and satellite images with even bigger pixel size, like 300 meters, 1 kilometer, 5 kilometers. It doesn't mean that they are not useful, of course, but they are useful. We can use them for different purposes. If you want to see shrubs, you go with this image. If you just happy with, I don't know, some forest area for whole region or for country, you don't need this image. You will be okay. You'll be happy with this 80 meters or 100 meter pixel. Okay, another thing, very important as well, is spectral resolution. It means how different properties, how different kinds of information about different properties we can get with this image. So actually, it's about the number and the type of the spectral bands, like we saw before, like blue, green, red, infrared, etc. So the more bands we have, the more information we can get. It's not like geographically detailed, but like thematically detailed. That's the point of spectral resolution. So this is like we saw before. If we have only visible bands, we can see less than we can see with visible and near infrared, and we can less with that comparing to visible and near infrared and short wavelength infrared, etc., etc. So this is spectral resolution. And just to show you example, the Sentinel-2 we talked about a bit. It has different like modes. So in the mode with the pixel size 10 meters, you have 4 really basic spectral bands, but we have another 6 additional bands, but with bigger pixel, 20 meters. But they are really okay. They're really useful for different purposes. Also, we have 3 additional 60-meter bands, but they are rather for corrections, not for gathering information about surface, but rather for like atmospheric corrections, something like that. So we have 13 different spectral bands, and we have several. When we have several bands, we can call it multispectral imaging, multispectral imagery. But we have also systems, also satellite systems, when we have dozens or hundreds even bands. So we call it hyperspectral imagery, hyperspectral imaging. And that might be very useful, not always, but it might be. We'll show you. So there we have like typical multispectral bands. So with this information, when we get the reflectance of different objects in those bands, we can get information actually like that. We don't, draw this nice line we saw before. We just get this information: reflectance in blue, reflectance in green, reflectance in red, reflectance in infrared for every pixel, of course. So with that, we can draw something we can call like spectral characteristics. For example, another pixel will look like that. Another pixel will look like that. So of course they're really rough, but that's enough in most cases actually. So we can see quite easily that is a vegetation, this is a bare soil, this is water, because we know that this is really typical. But sometimes the information we look for is hidden, very deeply in some really thin bands. For example, some, I don't know, minerals or something gives some reflectance, high reflectance or absorption in very, very thin band, the spectral band. So you cannot see it. You cannot, say that it occurred here or not with those like broad spectral bands, because this information is really, really hidden very, like thinly. So you need more of the spectral resolution. So you need hyperspectral imaging for that. And with that, you can, of course, recreate those characteristics much better than with typical multispectral bands. Another thing, temporal resolution. So it's how often we can take image of the point of our interest. For example, here we have some exemplary schedule of images. We took images in 1 month here and here and here and here and here and here. So 6 times we took image for the spot in May 2017. Actually, these are those images. So you can see that they are very clouded. Probably you don't have this problem, no, it's not as big problem as in Poland, probably cloudiness in Portugal, I suppose. But that might affect this temporal resolution as well. So it's not only how often we can get over the point to take a picture, but also how often we can use this picture. Here we can use only 3 of those 6 pictures. So the images. So actually this temporal resolution is lower than it could be actually. But it's not only a revisit time, this temporal resolution, because you don't have to go over the point to take a photo of the point. For example, I don't know, we took a photo of Lisbon today, and we need another one tomorrow. And tomorrow it won't be over Lisbon. It will be over Lisbon like 2 weeks. But we don't want to wait, so we can, for example, alter the optical axis with some mirrors or something. And when it goes, I don't know, over the Madrid, for example, we can alter the optical axis to take a photo, take a picture of Lisbon actually. So it might be improved, this temporal resolution, it might be improved like that, but it also can be improved by increasing the number of satellites in constellation. For example, we have this case in Sentinel-2. We have 2 twin satellites, Sentinel-2. So it's like that twice as often as one, obviously. And the fourth thing, it's not as important actually as the 3 before. Well, it's important, but the standards are really high anyway. So so it's radiometric resolution. It's how many levels we can write down in every pixel. How many levels of the reflectance we can, you know, we can see, we can write down there. Standard nowadays, it's like 11 bits or 12 bits, which refers to 2048 or 4096 levels. So it's a huge number actually. Typical image you see, I don't know, here now when you look at the screen, it's only 8-bit. It's only 256 levels actually. And even that is much more than we need. Human eye cannot see 256 levels of gray. Here we have an example of different images. Actually, that's the same image but graded from 8 bits, so it's 256 levels. And here we have 7 bits, which is 128, 47, 32, 16, 8, 4, and 2. Of course, we can see the difference here, but here it's really quite, well, difficult to see the difference between that. So we actually don't need this information with this 2000 or 4000 levels for ourselves, like for our eyes to look at it. But we might use it for different calculations, for machine learning. So it might be useful, and it's useful. So as I said, that's quite important, but for now, the standard is very high anyway. So it's 11 or 12 bit nowadays. Okay, we have some self-assessment questions, but we won't go through them now, for example, of course. We don't have a time, but you can download it, of course, those presentations. So just to, you know, just for you to be sure that you get the point. So we'll skip that and let's go to another part, radar imaging. That's quite different thing. Quite different area of this radiometric spectrum. Okay, so just because very often you might find called SAR. That means synthetic aperture radar. That's the same thing actually. Well, because the length of the antenna of this aperture affects spatial resolution. We should build like, I know, hundreds meters long antenna. We don't do it, but we like synthesize it during the flight of the satellite or of the plane. So this is why we call it synthetic aperture radar. That's just it, just to know what this acronym stands for. Comparing to optical images, radar images are completely different in, you know, almost every way we can imagine. So different wavelength, of course, different interpretation. It's not anymore the spectral characteristics we saw before, and also different geometry. So that's really, you know, like annoying. That make radar images processing really hard, real difficult. But also radar images have some really useful perks. One of them is that it is almost completely insensitive to clouds. So with that, we can have much higher temporal resolution. We don't have to worry about clouds anymore because it doesn't matter for radar images. That's really good, really important perk. Also, the system is active. That means that it doesn't rely on sun, on external light. It produces its own signal, and then it just receive it and register it. So no matter what are the conditions, if there is a cloud or if there is not a cloud, if it's a day or it's a night, we can take an image, radar image. So it's much better with that. Also, they have some really useful, sometimes useful properties, features, like it might, especially very long waves, radar waves. There are different bands. The C band, this is a band of the Sentinel-1. That's another Sentinel satellite. So this is C band. Longer bands can penetrate the vegetation, and sometimes even the soil itself. So, for example, we can evaluate, we can assess the condition of the soil, even if it's covered by vegetation. We cannot do it with optical images, but we can do it with radar images. Another thing which might be quite important when it comes to choosing radar images is called polarization. We can polarize this wave in different ways. Like we can have vertical polarization or horizontal polarization. Then we can polarize those signals when we emit it, and when we receive it, we can polarize it the same way. So we can call it co-polarization. We can cross polarize it, like vertically emitting and receiving it. We polarize it horizontally. That changed the way the signal responds to different classes, different types of objects. For example, here we can see the Sentinel-1, this VH vertically, horizontally, and here we can see vertically. They are different. They are the same date, the same moment, the same object, of course, the same area, but different images. And we can have in general like 4 different, like HH, VV, HV, and VH. So that's what we can have. And there are some satellites, some systems who can do it. They can do it, and that might be very important to interpret, to process those images as well. So we can create a color composition like that. And we can, of course, knowing how those different properties relate to different responses, we can interpret or process those images properly. Okay. About interpretation, what affects how we can see what we can see in the radar image. So the first thing, the most important thing, is dielectric constant. Like metal objects or moist objects, water, they reflect this radio waves very strongly, almost like 100%. For example, water reflects 100% of radio waves. But another thing important is roughness. So smooth areas they may, of course, reflect much of the signal, but they will be black in the image because it's mirror-like reflection. So it reflects and it goes other way, completely other way. It doesn't return to antenna. They're always side-looking radars because of some technical issues we don't have a time for. But with that, for example, for water, for smooth surface of water, it will go straight, completely different direction. And water reflecting 100% of this wave will be black in the image, which might be actually quite useful. And also orientation relative to antenna. Of course, if you can have a water which is oriented this way, okay, this will be bright. But well, unfortunately, we don't have this kind of water. So we have different types of reflection, like a smooth surface, like scattering. So, for example, when the surface is rougher, some part, at least some part of this wave, of the signal, returns to the camera. So rougher surfaces will be brighter in the image. Also, we can have some corner reflection, like for example with buildings, and this kind of structures will be very bright in this co-polarized, like VV or HH, co-polarized images. For a change, this kind of scattering, volumetric scattering, will produce very high response in this cross-polarized, like VH or HV. So different, like geometric structure, geometric properties of the objects affects how they look in different images. So that's a completely different thing than we had with optical images. Okay, I just check what time is it. Okay, not bad. Let's go to radar interferometry now. Because that's another perk of the radar interferometry. It bases on wave interference, which is, well, like we throw two stones into river. We can see that sometimes they make them higher, sometimes they suppress themselves. So it works that way. Sometimes they enhance when the phase is the same, and sometimes when the phase is in opposite phase, the wave is in opposite phase, they suppress it. So the result wave is like much weaker. So it works exactly the same way, actually. So we need like two stones in the lake, in the water. So we need like two satellites, or at least one satellite, but in different positions, of course, in time. So this way we can see that there will be parts which are enhanced, and there will be parts which are suppressed. So when we take like two images with this kind of data, and we compare what was the meeting, where they meet, where they enhanced in this part, or when they where they suppressed when they meet the ground, we can create something like that. That's called interferogram. So we can unwrap it to something called digital terrain model. So with that we can create information about the lie of the ground, about the relief. We have quite a well-known mission, SRTM mission. It's a shuttle radar topographic mission. That's NASA one. So it produced this way, actually this produced digital terrain elevation data. It's not very detailed. It's 90-meter spatial resolution for the whole world and 30 meters for USA. But anyway, it's free, so it's not bad. But even more interesting thing about this radar images, I think, it's something called differential interferometry. Its accuracy is much higher than INSAR, than this normal interferometry to create those digital terrain models. What is about? So we get this information as before. We get the information about the phase of the returning signal, receiving signal, and after some time we take another step, like a picture. Well, let's call it a picture. It's not actually a picture, but we get this signal again after some times. But let's imagine that between those times something changed. There are some displacement or whatever. So when we take it again, the phase of the signal will be different than before. So we compare those phases, and by comparing those phases, we can calculate, we can measure actually this displacement. That's almost the same thing. So it's very accurate. Actually, it's about millimeters. That's meters for this creation of digital terrain model, and it's millimeters for this differential interferometry. So again, some self-assessment questions for you for later. And another type of imaging thermal imaging. So it's called thermal infrared. That's another type of infrared that's completely different than those infrareds we talked about before, like near infrared and short wavelength infrared. Actually, we call it infrared because it's like longer than red, all of them. But that's like a different story actually. That's completely different than others because it doesn't register the signal which is reflected by the object but emitted by the object. So we actually it's like a great really big thermometer. So we can, for example, produce some heat maps for like cities. We can perceive some very bright, so it means like hot, warm objects. So this is how we can use it. Actually, the spatial resolution of thermal infrared bands is very low. Actually, for Landsat 8. This panchromatic image, it means it's an invisible part of the spectrum. It's 15 meters, and this thermal infrared band is 100 meters. So it's much worse actually. But it's okay. That's enough for a lot of purposes. And for the last part of this first part, laser scanning. So that's not actually like images. We don't produce images. It's light detection and ranging. That's about ranging rather than about images. So this, we call it LiDAR. It's like radio detection and ranging. That was radar. And LiDAR, it's light detection and ranging. It doesn't base on radio waves. It's based on light. It's based on sometimes green, sometimes near infrared light, on laser actually. So its purpose is to emit the signal, the laser signal, and then to receive it, and then to measure the time between emission and reception. So doing that, we can calculate the distance between the scanner and the objects. And doing that, when we can calculate, we can localize the scanner very, very precisely with very good accuracy using like GPS and other types of tools. So we can calculate very accurately the height, the altitude of the objects. Laser scanning might have also very interesting parts like this one, for example. We can receive the first reflection, but also we can receive and register the second reflection or the third reflection and the last reflection. So doing that, we not only can calculate the height of this the altitude of this tree, but also of the ground. So we can, for example, knowing that, we can like remove those trees from the picture. We can like look beneath those trees and get the information from beneath from the ground. So this is very very useful for creating 3D models. Like we have tree and a building here, and for example, when we get the first reflection, we create something called digital surface model. But when we get last reflection, we can create something like digital terrain model, but with buildings. Digital terrain model would be like that, would be without this building. Of course, we can get the last reflection because building is not, as transparent as tree might be, but we might filter it out. So we can create digital terrain model, actually real one. So they are very useful for that, but not only actually. For example, with this something called full waveform LiDAR, we can like register not the first reflection or the second reflection, but whole function of reflection. So comparing different, for example, tree species, we can see that different species have different waves, different forms of those waves, different functions. So we can like actually classify tree species using this full waveform LiDAR. So some examples how it looked like, because actually we don't have an image like a typical image with pixels and all the stuff. We can create it, we can generate it from this data, but in this first raw form, it's like a cloud of points, like 3D cloud of points with different features. Of course, X, Y, Z coordinates, and sometimes you use also intensity of reflection. It might be also very very useful. For example, here that's active system again, like radar systems. So doing that, we independent completely from external lighting conditions. So for example, this is an example of multispectral laser scanner. So we don't have only this information about altitude, but also about some spectral data, which is like comparable to optical images. Okay, so this we have also satellite lidars, but they are used rather for like bigger scale projects. For example, to monitor movements and changings of huge parts of land, for example. So airborne lidars can have really great big accuracy, and satellite lidars not so good. Okay, so I think that's enough for the first part. So I stop sharing the screen, this black screen. Okay, I'm totally black. It's already 6 in Poland, and yeah. And we quite a big off. So let's have a 5 minutes break, okay? And
okay.
Again, I please I beg you, leave some. I saw that there were some comments. I didn't have time to look at it. Okay, the relation. Okay, we can. I have a proposition. So I have those two questions. So we may discuss it during this break if you want to, or we may discuss it later. Like I can write an email to you or whatever you want actually. So again, please write down in chat box, or please do it in this evaluation form what is interesting for you, and we will tailor make your course in the future. Okay, great. 5 minutes.
And we return
in Poland.
Okay.
Great.
Thank you.
Okay. So see you.
Okay, it's better to take a break. So I think we can restart.
Great. Francesca, you had a question. I answered it. Yes, it is always like this. It's always connected, you know, that geometrical thing. So it's always like 3 times actually. It's two times root square of 2. So it's actually that. I will be happy to show you why actually, but maybe later. That's very interesting, in fact. Okay, I changed the cursor to make it greener and bigger. I hope it will be better now. Okay, so let's go to the second part. First, we will talk about how we can get information, because what we had before was about data, about like raw data. But how can we know what's there actually? How can we get this information from this data? Then we talk about Copernicus Program, few words, and some examples of applications. Okay, so how to get information? Actually, we can get three different ways to do it. In general, the first thing is visual interpretation. It's just looking at the image and interpretation, mentalizing the information, you know, producing it in our mind. It's just we look at the image, we see what we see, and we interpret this information, we mentalize it. Sometimes you use also different external information, knowledge, etc. for that. And those image things, those features of objects, we call them interpretation features, and they might be like color or tone, shape of the object, its size, texture, structure of the objects rather than one object, neighborhood of the object, etc. So when we look at this image, so of course, first we see the colors, so we can say, okay, this is dark blue, so it's probably water. This is pink, so it's probably, well, I would say that's oilseed rape. This is forest because we can see the texture. This is road because it's long and narrow and thin, and well, and that's how we interpret the image. Beside that, we also use some general knowledge or knowledge about this specific part or this specific, you know, time. So like historic, physiographic, environmental, etc. context. So that is also useful, and we sometimes use it as well, if we can, of course, we have this knowledge. This process is very accurate because we take into account all of this interpretation features, all of our wisdom or of our intelligence, our experience, we can use it, but also it's very time consuming. And even if you are very quick, you know, and we are very experienced, and we see like in a moment what's there, and it's not a problem, we just mentalize this information. So if you want to like share this information with someone else, we have to like translate it to digital form, we have to digitize it, we have to vectorize it. So it takes time. We have to take a mouse, we have to, or a pencil, we have to draw the lines, and we have to show that, okay, this is water, even if we know it instantly. So that's very time consuming also, but well, very accurate as well. Okay, so you can just read about interpretation of remote sensing images there. And another way to retrieve the information is something called spectral indices. They are actually sometimes very simple, sometimes more complex, arithmetic processes of different spectral bands. So that's why we call them spectral indices. So we retrieve the information about those objects, basing on our knowledge that different spectral bands contains different kind of information about different objects, and that different reflectance, that means how bright or how dark the object is in a specific band. So that's the reflectance. So we know that different reflectance means different things. So we combine them and we retrieve the information about different things. We have like vegetation indices, very popular and commonly used. We have moisture indices, we have soil indices, and you have many, many more indices, actually. Let's start with this vegetation indices. In general, they base on those two bands, near infrared band and red band. Vegetation indices might serve different purposes, but for example, like the first easiest thing to do is to differentiate, to distinguish vegetation from the other types of classes of land cover. So we can see that this contrast, this relation between near infrared, very bright, vegetation is very bright in infrared, and red, it's very dark for a change. So this contrast is, well, let's say like unique. It's different. It might help us to distinguish this class of land cover. So that's the first thing that we can, for example, you can see that it's not as that. We can like calculate the difference. We can calculate ratio between those two reflectances, and it will be much, this difference or this ratio will be much higher than for any other class of land cover. But also when we compare it, this dry vegetation, for example, to this vegetation, the healthy vegetation to dry vegetation, we can see that we can also evaluate the condition of the vegetation. So vegetation indices might serve just to like identify vegetation in general, but also to assess, to evaluate the condition, to monitor the condition of vegetation. So one of the most, well, it's like, it will have in 2 years, I think it will, oh no, in 3 years, it will have 50 years. So it's 47 years old, this vegetation index, normalized difference vegetation index. And its formula is very simple, very easy. So this NIR stands for reflectance in near infrared band, and R stands for reflectance in red band. So we just take near infrared image, we take red image, we calculate the difference, we calculate the sum, we divide one by other, and we have NDVI. We have every pixel with different value, basing on those relations between near infrared and red. So we get this information, and it's information because it's just one number. We don't have to interpret it anymore. It's just a value which tells us how many, well, let's say biomass we have here, how much vegetation we have here in this particular part of our image. That's one of the probably most popular, but just one of many. We have like, I don't know, probably hundreds of vegetation indices. How it looks like, well, we have red image here, we have infrared image here, and we just process them together, and we produce another image, which is not red or infrared, it's NDVI image. So whatever is bright here, it means that the brightness means higher value of the pixel, which means that that this vegetation is healthier, there is more vegetation, so those bright parts of the image are probably covered by vegetation, by healthy vegetation. This like light gray is probably, I'd say, forest. Those dark areas are water, or sometimes you can interpret it by the shape, probably bare soil, so it will also be dark. So this is NDVI, one of many vegetation indices. Very simple to calculate, very easy to interpret. So this is why it's so popular. There are more sophisticated formulas also in the market, let's say, but that's one of them, and because it's so easy, so simple, it's so popular. So we can evaluate the vegetation condition and also biomass. We can see here the relation, the correlation between NDVI value and leaf area index, which tells us about biomass actually. So we can see that this relation is, well, is quite significant. There are some problems, it's not perfect, but it's a good way to assess, at least, you know, roughly what biomass we have there. So for example, with this NDVI value, we can predict yields like in advance, like 1 to 3 months. So it might be actually very, very useful. We have also moisture index. They actually, we can use them also to evaluate the condition of vegetation. And actually they are even better than those vegetation indices basing on near infrared and red. So the problem is that we need to have middle infrared. When we have middle infrared, it's okay, let's go to moisture index. If we don't have, well, we have to be happy with this vegetation index. So, for example, in Sentinel-2, this satellite we talked about, there is a middle infrared, so we can calculate it, but only in this 20 meters mode. So if you want to have vegetation index with 10 meter pixel, we have to calculate vegetation index like NDVI. We cannot use it because it's 20 meter, for example. So this is very, very useful index as well. But as I said, there are many others, like here, for example, this is some great, well, not great, quite big, like a lake in the north of Warsaw in Poland. So this is an index to assess, to evaluate the quality of water. So we might use also water indices. Like here, those numbers here are the means of the bands we use. Like there we have like near infrared and red. So we have those bands written down here. And quite an interesting thing here, that's to assess chlorophyll in water, the amount of chlorophyll. You can see that those bands are very, very close to each other. You see, it's like 6 nanometers, that's nothing. Normally, those multispectral bands have like 100 nanometers broad bands, actually. It's like from 400 to 500, from 600 to 700. Here, we have to use hyperspectral data. Without it, we couldn't calculate it. So that's an example of using this hyperspectral data. Again, self-assessment questions for later. And I hope useful links with a really long list of those indices. And probably the most sophisticated and the most interesting way to get the information, machine learning. I don't know if you're used to this term or this idea. Actually, that bases on memorization of patterns by the machine, of course, experienced by the machine. It means that we may probably for example, show to the machine some examples of different classes. So we can show the patterns and it, well, let's say memorize it. It learns how different classes of objects look like, and then analyzing new data basing on what the machine learned. So this is how machine learning works in general. Let's look at this very simple example. We have like very small image here, 20 pixel. Each square is a pixel. We know that this color image is consists of 3 different bands. So it consists of red band, green band, and blue band. Of course, every color is like a combination of those 3. So we can say that every pixel has its value in different band. Its value refers to the brightness, to the reflectance in this particular band. So we can call those numbers, those value, we can call features. And then let's imagine something we will call feature space, which means that those features will be like coordinates in this feature space. For example, here we have red dimension and green dimension, which means that whatever is like bright in red will be high here, and whatever is high in green will be on the right of this diagram, and whatever is dark in green it's not green. It doesn't reflect green light. It will be on the left part of this diagram. So this way, when we reorder in this way, like those numbers are actually coordinates, we'll have something like that. So similar objects, similar elements actually, so similar elements will be close to each other. Like those pixels of the same almost colors will be very, very close. So you can say that the proximity in this feature space is like resemblance of different elements of the set of the image. So this way we can, for example, group those pixels, or we can like draw the lines, and we can say, okay, this part of the feature space, whatever is there, whatever is put there, we can call it red pixels. Whatever is there, we will call it orange, and green here. And that's actually some basics of the machine learning. Of course, that's not machine learning. Well, this part is not machine learning, but machine learning bases on those different features. So another thing is, of course, how to teach machine to recognize patterns. For example, we could say, okay, so look at this one, look at this one, look at this one. They are like three patterns of different classes. So after that, we just compare different elements to those patterns, and that's how we like classify the image using machine learning. We have different types of features in remote sensing. Of course, we have spectral features, which means the reflectance in different spectral bands. That's the easiest way to calculate, to classify the image, because actually the spectral features is the first thing we have like in the raw form of the image, and the only actually thing we have in this raw form, because every pixel has its values, and every value is a spectral feature. We can have different spectral features, of course, like blue, green, red, near infrared, etc., etc. But that's just spectral features. But beside that, we have spatial features, like those interpretation features we saw before, like shape, like size, like texture. So we don't have it written down in the image. We have to process it somehow to get this information. It's not that easy. Well, it's doable, of course, but it's something more. We call this kind of classification, which might be based on those spatial features, object-based image analysis. We'll talk about it in a few minutes. Also temporal features, which might be very useful, and altitudinal, adding, for example, information about height, about altitude from LiDAR data, for example, like we saw a few minutes before. And what about those spatial features? So let's imagine that we have different groups of objects, and well, you can see that yellow circles, blue circles, yellow triangles, and blue triangles. So using only color, using only spectral features, we cannot divide them into 4 classes. We can divide them only basing on color, only divide 2 classes, like yellow objects and blue objects. But when we add another feature, like a spatial feature, shape feature, then we can divide them. Then we can distinguish 4 classes actually. So we can distinguish yellow from blue using spectral features, but we can distinguish circles from triangles using spatial features. So very often we use them together, and that's quite a nice combo when we use them together. That's a very simple example how we can do it. That's just the spectral data, the image in this false color composition we saw before. So the red color means vegetation. This like gray blue color, it's here it's bare soil. some plot. There we have some build-up area, forest there, etc. Water for sure. So when we classify this image basing only on spectral features, it might be difficult to get the accurate result. Look here, this color here and the colors there, they are very similar. So it means that basing on only these colors, we might be, very inaccurate in this part. So that's the result of this kind of classification. So we have this build-up area almost totally misclassified as bare soil. It's brown. It should be gray, and it's not. Well, so that's just one example. But when we add another information, textual data, and this textual data is retrieved from this image itself. It's not any external data. It's just the image processed, and we get something like that. Well, it might not look very informative, but it is, believe me. So when we join the forces of spectral data and textual data in something called spectrotextual classification, this is the result of granulometric analysis, by the way. One of the methods of texture analysis. So when we get them together, the result might be much better. Like here, this is not anymore bare soil, but actually the build-up area. So this is well, the comparison how it improves the accuracy of the classification. So that's one way. Actually, texture analysis is very well. Textural data in general is relatively easy to get from the image. But when it gets to things like size of the object or its shape, it's much more difficult. And for that, we need something called OBIA, or object-based image analysis. Sometimes we call it GeoBIA, so it's geographic object-based image analysis. Anyway, it's an object-based classification, object-based image analysis, and it consists of two steps. The first step, it must be segmentation. Because when we want to take into account features like size of the object or its shape, we have to get the information where the objects are. So this is what segmentation is for. So that's the first step, and the second step is the classification itself. But we classify not pixels like before, like with the spectral data, because we take pixels and we say, okay, this pixel is in this class. Here, we don't classify pixels, we classify segments. We classify those objects retrieved from this first step. Sometimes we call this segments, we call them super pixels. So that's like elements of the object, but containing like smaller elements. So this is image segmentation results. So we can see that you have different objects here, so we can calculate those their shapes, for example, in different manners. We can calculate easily the sizes, but by just counting pixels within those objects. So we can get much more from that. We can take almost everything into account, almost everything from those interpretation features we talked about when we talked about photo interpretation, visual interpretation. So that's it. But also we can use temporal features. Sorry, just to, what time is it? Okay. We can use also temporal features, which might be very useful. They are useful, especially when it comes to classification or to identification, to analysis of objects which are very dynamic. For example, crops. For crop identification, we need to have multi-temporal series of images. We'll talk about it in like 15 minutes probably when we go to examples. So just a simple way to show it. That's image from April, image from June, image from September. We can see that it changed. It changes differently actually for different parts of the image. Sometimes it's always red, for example, like I don't know, like here. It's always red in every image. Sometimes it changes from red to blue, sometimes from blue to red. So this is this profile, this pattern, this temporal pattern we can analyze, helps us to identify what's there actually, what type of crop, what crop species is there. So we can also create color composition, not only from different bands, but also from bands from different dates, like here. So actually every color, each color here means different pattern, different temporal pattern, not different spectral pattern like we saw with this like true color or false color composition. This is temporal pattern shown there. And altitudinal features, that's quite simple. For example, we can use this LiDAR data together with spectral data. For example, we can imagine that, I don't know, we have roof and road in the same image, and they are both covered by tarmac or something. So they are very similar spectrally. So we could misclassify them basing only on spectral data, but adding this altitudinal data, this height of the object, we can say, okay, it's higher, so it's probably building, and it's low, so it's probably road. So we can use really a lot of different features, different types of features for this remote sensing. But also when we talk about machine learning, it's also about different approaches to learning itself. So it might be unsupervised when we just let the machine to recognize the patterns by itself. Sometimes we call this unsupervised methods as data mining. We call it data mining because it mines for data. Sometimes it's even difficult for human to to browse through all the features we have, to all the data we have, to see the pattern by yourself. It's sometimes difficult. So we might use those unsupervised learning to learn those patterns for us, to show us where the patterns are. Sometimes it's much more effective than just browsing and interpreting like image or like table with like millions of records. But probably much better, much more effective, and much more accurate is something called supervised learning, supervised classification. For us in remote sensing, it's well, we can show it like here. We have the image. We know, because in unsupervised classification, we don't tell where the patterns are, what classes we want to get. Here in supervised classification, we exactly know what we want to retrieve, what we want to get. So for example, we show different places, different samples of different classes, and we showed, okay, so this is water. So we show, okay, this is water, land, this is water. This is water also, this is like low vegetation, this is bare soil, this is forest, etc., etc. So we show those patterns, and during this machine learning process, there are a lot of different machine learning methods, and it's very, very interesting, by the way, how different they are and how smart sometimes they are. By this process, it learns how to recognize different classes. It learns how to retrieve those, let's call them signatures of different classes. And after that, it compares every single pixel, every single element of the image to those signatures, to those patterns it learned before, and it classifies the image. And that's the result of this classification basing on this part. So we, of course, we are needed here in this process, because we have to teach actually machine to recognize those patterns. But this learning might be much quicker than visual interpretation. We don't need to to draw the lines to digitize every single object. We just show some really small samples, and sometimes that's enough. Of course, it's not as accurate as photo interpretation, as this visual interpretation, but it's much quicker. And it might be especially important because of the amount of data we can use. We have like terabytes every day produced by Copernicus Program. We will talk in 3 minutes. So to visually interpret it, it would take ages. It wouldn't be possible actually. So we have to use machine learning. And we have different algorithms, different methods, from very simple like k nearest neighbors or minimum distance to very, very smart, more advanced and very effective methods like random forest or support vector machines. That's one of my favorite issues actually. To very complex things like deep neural networks. Deep neural networks, deep learning, we call it sometimes deep learning, is something much more different than the machine learning we saw before, because in this deep neural network, we have something called hidden feature engineering. What does it mean? This unhidden feature engineering means that we know exactly what types of features should be taken into account, even if it's unsupervised learning. So even if the machine learns those patterns by itself, we always show, okay, take into account blue, green, red, near infrared, etc. So we tell the machine what to take into account. But within deep neural networks, we have this hidden feature engineering. So it means we don't know actually what it will take into account. We just show, for example, it's like learning, like normal learning. Well, I suppose we won't test it, but I suppose that every one of us can, distinguish, cat from dog. Okay, that's probably not a problem. And I don't think you remember when you learned how to distinguish cat from a dog, but I suppose it wasn't like that. Like someone told you, like, I don't know. Okay, so count legs and then count ears and look at the shape of the ears and at the color. You just saw like hundreds of cats. You saw hundreds of dogs, probably in books at the beginning. And this is how you learned it. Actually, it would be quite difficult to tell someone else how to distinguish cat from a dog. I really couldn't do it. Probably that's this hidden feature engineering. So we just showed to this deep neural network. We just showed the object. So we just showed the image, and we say, okay, this is forest. We don't know how to recognize, but we know that this is forest and this is water. So learn how to recognize it. We don't care. Do it for us. So it might be very powerful. It might be very dangerous, because when we don't know what it takes into account, it might do some really bizarre things. So I would be happy to tell you about something more. We don't have a time, but if you're interested in that, please contact me and we'll discuss it later. We'll continue it, I hope. Okay, so self-assessment questions. That means that we go to another part of the presentation, which is Copernicus. Copernicus is like a Dutch phrase, Europe's eyes on Earth, and that's actually what it is. It's managed by European Commission together with European Space Agency and together with European Union member states and also some organizations. It consists of two components. Space component, it's responsible for data acquisition, and ground component responsible for data storing and processing. So about the space component, finally we'll talk a bit about Sentinel. The very heart of the space component, and actually of the Copernicus program itself, is the family of Sentinel satellites. There are 6 types of Sentinel planned, or even more actually. For now, we have 4 types of satellites in orbit. 7 satellites of 4 types, like we have 2 Sentinel-1 satellites, 2 Sentinel-2 satellites, etc. So they are different satellites. Like for example, Sentinel-1 is a radar satellite. Sentinel-2 is optical satellite. So we have those blue, green, red, near infrared, middle infrared, etc. bands. But we will have also some different satellites for different purposes. Like for example, for atmospheric monitoring of atmospheric pollution. There will be thermal scanner as well in the future. So we'll have really nice, rich information, nice data set we have now actually. So as I said, like terabytes of data produced every day by Copernicus, by Sentinels as well. Also, beside that, that Sentinels, which are like raw data, so we can download it, we can use it either way. We'll talk about it, by the way. Beside this raw data from images, we can also use some Copernicus services. Those services can help us, provide us with information, with products, with ready products. We don't have to analyze it. We just may use it. There are 6 different services. Let's look at 2 of them. CAMS, which is Copernicus Atmosphere Monitoring Service. So it produces everyday maps of different kinds of pollution, atmospheric pollution. Like here we have this aerosol with different dates, so we can set the date, we can set the type of pollution, like carbon monoxide here. Like you can see, we have like quite a not nice situation in Poland. It was in July. Wonder why? Oh, it was much better week later. Okay, so this is how we can use Copernicus program as well. So products ready to use. CLMS, which is Copernicus Land Monitoring Service. There are different products as well. So for example, Copernicus Land Cover, the CLC stands for Copernicus Land Cover. This is a map of the whole Europe, consisted of 44 classes of land cover for different dates. You can see there. So we can open any date, any part of the Europe, and we have quite a nice information about it. We can download it. We can use it for some web map services, for example. Well, that's a product again we can use. Also, we have something called high resolution layers. So there are information about forests, about different types of forests, about grasslands, about different things. Okay, and let's go to the examples of applications. I hope we will, we'll get it to the end. So I have 4 types of applications presented here. Actually, this will be very, very brief, like browsing through them, because we could talk like 5 or 8 hours about agriculture itself, probably, because the list of possible applications of remote sensing, particularly in these fields, are really vast, really long, actually. Okay, agriculture. Like 4 different, we'll present 4 different examples. Precision farming, that's probably one of the better developing applications of remote sensing in agriculture. It starts, what is precision farming for starters? So it's a farming, but precise, which means that we don't use, like we don't work the same way in on the whole plot and the whole parcel. We use different amounts of different products like fertilizers or plant protection products. We use it the amount we want in the places we want, actually, the amount we need the places we need. So for that, we need precise information about the condition of the soil and about the condition of the crop, of the plant. So for that, we need remote sensing data like satellite images. For example, NDVI images, we can calculate it to assess, to evaluate the condition of the plant. So using this kind of data, we can produce models to produce application maps. Those application maps show us exactly where to put what kind of product in what amount. So with this application map, we can use, of course, specially equipped tools like with GPS, of course, and with different, agricultural stuff to sow, to fertilize, to spread plant protection products exactly where it's needed. Sometimes the plant is well developed in one place, so it needs less of fertilizers. Sometimes it needs more, so we put a lot of fertilizers there. So so we can save a lot of money and a lot of environment actually using this precision farming. After that, we can also after all this this process, we can also yield the yield and monitor the yield, creating something called yield maps, just to analyze what was the result of our modeling, of this first part of modeling, and to actually to improve those models for the future. So that's the circle, and the remote sensing data is very important because only remote sensing data can help us to get information about the condition of vegetation for this purpose. Crop identification, we talked about this, that we need multi-temporal series of data for that. Actually, we need the highest temporal resolution possible. So if it was like every day, great, we could use it. Because that's a very difficult task actually to do, but well, to some extent possible. So we can see some different crop types like spring wet, winter oils, seed rape, and permanent grassland. So we can see that this pattern, of course, this red means that there is a vegetation. This blue means that the gray blue means that there is no vegetation. That's bare soil. So we can analyze those like profiles, those temporal patterns, and we can this way we can identify different crop types. So this is how we can do it. As I said, we need very high temporal resolution. So very often we use also radar data, because radar data, it's insensitive to cloudiness, and clouds sometimes are a very big problem. So to fill the gaps, we use those radar images as well, and it actually improves significantly accuracy significantly. Okay, another example of application: agricultural insurance. We already know, I hope, that we can analyze crop condition using remote sensing, but also we can analyze it. We can monitor throughout the entire season, which might be very, very helpful. For example, let's look there. We have the very damaged parcel. We can see that this is NDVI image. Those green parts are the high vegetation, high NDVI values. So it means that the condition is very good. Those yellow and red or orange means that the condition is bad. So probably the plant is damaged here, but we can also look back, and analyze what happened before. And we look at this red image, what it's with points, but also we have different things like there. So it was like damaged. It was in bad conditions, in bad condition before. So for example, we can say, okay, so this damage wasn't caused, for example, by frost. It wasn't caused by bad wintering. It was caused by something else, because maybe that's the problem with this place. Maybe that's your fault. whatever. That's not the problem. That's not the issue. The factor you were insured for. So we won't pay you for this, but we will pay you, of course, for this part because it was in perfect condition. It's bad. So okay, it was damaged, but not this one. So we might use this information this way, and also and also to monitor good agricultural practices. That's maybe more for some I don't know, government agencies managing those areas, probably. So how we can use it? Of course, again, we need to have multi-temporal data, but not as dense, temporally as before with this crop identification. So with that, we can easily perceive, we can easily detect some whatever happened actually in the parcel we monitor. So for example, tillage here, we can not only say what happened, tell what happened, but also when did it happen. So like a mowing here, for example, in some grassland. Sorry, too much talking. Okay, we'll manage. That means that we go to forestry. Forestry have also a lot of different applications. For example, here is another service, that a product ready to use. That's not Copernicus program. It's provided by University of Maryland. But here we have we can visualize and download as well maps of different information about forests, about forest loss, for example, forest gain, forest extent, etc., for different dates, for different areas. Also, there are some example locations, so we might find some interesting things. I mean, the providers find interesting. So that's the one example of that. That's based on Landsat imagery. So this is NASA, well, also NASA, yeah. NASA American, I mean, satellite. It's also for free. The images can be downloaded and used for free. So we might produce the same information as it's here. And it's powered by Google Earth Engine. It's one of the cloud platforms. We will talk about cloud platforms in a minute. So it's one of them. Yeah. And another example, we had that's not common in Poland, so that was quite an event. We had a relatively big hurricane in Poland in 2016 in Supraśl. That's a town in northern part of the Poland. So we have the image before the hurricane and the image after. You can see here we have some magenta, some violet colors. That means that it's damaged. Actually, we can better compare it in NDVI images. We can see that there are darker parts here, so it means that this part was actually deforested. So using these images, we can again those parts here and here, we can calculate the area, we can measure the area, we can assess the damage done by this hurricane or whatever else actually. Quite a vast list of applications we'll find in crisis management as well. Well, that was actually one of the examples of crisis management. So of course they are, like sometimes in like both fields. So we can monitor the occurrence and spread of natural disasters like fires, hurricanes, floods, etc. For example, here we have an example of a huge forest fire in 1988 in Yellowstone National Park fire in Yellowstone National Park. And that's an image taken before, a year before the fire. That's taken during the fire, and that's a year after. So you see how vast damages were done by the fire. So we can, of course, again, assess the losses. We can say what happened. After that, of course, we can also use those images, the satellite images, to monitor the way it recovers. So well, we can use it for this crisis management, and after that for monitoring what happens after. Another service, quite interesting, fire information for resource management system. So we have a map of fires, well, happening now, of fires like in the past. So well, that's another way to manage crisis. Actually, this information, this service is based on images of very low, actually, spatial resolution. You can see here it's 375 or 250 meters pixels. And flood monitoring. Here we have that's a radar image. At last, so we have this image before flood and image during flood. We said before that the water reflects the like full amount of radar waves, but in completely different directions. So we have something like that. So the water will be black, which is very helpful to monitor it, actually, using those radar images. Or this example, we have again color composition, and this is like temporal color composition. In blue, we have an image before flood, and in green and red, we have an image during the flood. So how can we interpret this image? We have those blue colors here, blue areas, which means that they were bright only in this image in blue, so only before flood. They were bright before flood, and they are not bright during flood, which means this is only blue. You know, this blue consists of only blue, not green or red. We can see that. So it means that they are black, actually, in this red and green. They are completely dark in this image. So it means that they are covered. They are covered by water now. They are flooded. But they weren't flooded before because they were bright in this before flood image. For a change, we have this black part here. For example, this water, this river here. It's black. It means that it was black before flood, and it was black during flood. It is black during flood. So this is where the water is supposed to be, actually, and this blue part is actually flooded, like in extents. Flooded area. Or the example here, also with water, that's the ocean, and those black areas here. This is a spilled oil, actually. What happened here? Normally, we said that the water is black, but not always. When the water is like ondulant, like we have waves, so it's rather like a roughness. This waves make it rougher, we might say. So this ondulant water won't be like perfectly black, but the oil spilled on the surface increase the surface tension, so it makes it smoother, so it makes it black, actually. So we can monitor the oil spills. That's probably some ship, and it spilled this oil here. Okay, and the last thing, infrastructure monitoring. So, well, we can do it like in different ways. We can just create land use, land cover maps, for example, and then monitor changes. So that's one way. So we can use it. We can do it using optical images, for example. But the more interesting, I think, for now is this deformation and displacement monitoring. We can use it. We can do it using this differential interferometry, especially like a special case of that so-called persistent scatterers interferometry. So it means that we have a list, a map of persistent objects, or like you know, very solid objects, persistent scatterers, which means that we can define them, you know, throughout the years. Always they are in the same way in the image, but we can base on those persistent scatterers and monitor their displacement. So doing that, we can monitor, like and indirectly actually, displacement of the ground itself. So it might be very helpful to monitor the infrastructure. Yeah, like here we have some, I don't know how it's called actually, something. So this is like a model, and this is whatever. Or here in Amsterdam, just an example. So we can see that the accuracy of that is, like, precision is very, very, very fine. It's like 4 millimeters, like 1 millimeter, 2 millimeter per year. That's the accuracy of this method. So another example, mining damage monitoring. For example, here, very, very accurate comparing to precision surveying. It's almost the same thing. Or dam here, just a few examples. Okay, so self-assessment questions means that we stop sharing this presentation and quickly switch to the third one, and the last one actually. The third one is there. Okay, I hope you can see it. Let's hope it will go. Yeah, great. So part number 3, we will talk first about CREO-DIAS platform, about this data and information access service. And after that, we will talk a bit about Galileo, about European satellite navigation system. Okay, so DIAS, as I said, stands for Data Information Access Services. It's like a huge project financed by European Commission and European Space Agency. And it completely, there's a question. Do you want me to answer it? I don't see it. Okay, maybe later. Okay, sorry. So let's go back. It changed the way we work with our data actually, because like a traditional way to use it, like we have Data Hub, like for example, Copernicus Science Hub, we can download images to our local computer and process it there, here where we're sitting. But DIAS is for something, well, different and actually better, because DIAS concept bases on the concept that we analyze the data like in a place. Like we don't have to download it to our computer. We just need the computer, for example, to download results, or just only to order to supervise what we want to do. But everything is there. Everything is in DIAS. We don't need to download this huge amounts of data, and sometimes it's really huge. It's like not gigabytes, like terabytes. Sometimes we need to to make analysis. So we don't have to download it. We don't have to buy to create infrastructure in our place. We can use the infrastructure already there. So this is what this DIAS for. This is CREO-DIAS. This is one of the 5 DIASes I want to talk about. It's created by a consortium of those 6 partners. We will find a lot of data there. Like satellite sentinel data for Europe. We have everything, and this SLC, that's the important thing, especially for this interferometry, because SLC stands for single loop complex, and that's the product containing those information about phase, which is important for this interferometry, which is crucial. With this grid, we have only images, we have only intensity. We don't have phase here. We don't have phase here. So if we want to calculate interferograms, we need to use this data. So we have this kind of data. We have also not only Sentinel, but also Landsat images for Europe again, and also some other satellite data, but not only satellite images, but also some different models like digital elevation model we talked about and more. There are also some Copernicus services, so we can use the products of there. You don't need to, to download it or something. It's already there. We can use it also together with our images, and the processing is, as I said, online. So you just say what you want, and it's done there. We can use we can use a software like popular software like ArcGIS, QGIS, etc. We can produce our own tools if you want to, and there are different functionality levels there. Probably the lowest one is CrowdIAS Finder. You can register there in a CrowdIAS for free, and you can use CrowdIAS Finder. It's just for searching data. You just choose the area, you just choose the collection, which means the satellite you want to take data from. You choose time range, cloud coverage. For example, you want like only 10%, not more, of clouds there. So you just set all there, and you get the list of the images meeting the requirements you set here. So that's one way to use it. We have also CrowdIAS browser. CrowdIAS browser is for searching and visualizing as well. So again, we can choose what satellite we want, cloud coverage, we set time range, and then we can find those images, but also visualize it. Visualize it in different manners, like true colors here, or false color, or NDVI. It's already there, so we can easily visualize it. We can create our own composition or even our own index, spectral index if you want. There is a tool for that. So that's another way to use it. And probably the most advanced way to use CrowdIAS is a possibility to create your own front office. You just create a result, and you might present and share it with the world in the manner you choose actually, and even commercialize it. That's the example of that. So for example, that's a reticus based on CrowdIAS, and this is this displacement for mining damages, mining areas, basing on persistent scatterers, by the way. There is a film showing us what we can do, so I don't think we have time actually for that. That's just a very powerful tool to do it. So we can create diagrams, we can create profiles, we can visualize maps, etc., different kinds of information, of course. So let's go to another part, billing models. So I don't think we have a lot of time, but I hope it's not a huge thing if we just extend 3 minutes. So billing models, how can we use it? Of course, we can register for free, and we can browse through the images for free. But if you want to use it, we can pay, for example, per hour or even per minute. But also there is a possibility to fix the terms for long-term contracts. And also another interesting model, it's revenue sharing model. So you just sell it and just share your income with CrowdIAS. So that's another way to use it. There are other DASs, these four, not only CrowdIAS, and also there are other platforms, cloud platforms like Google Earth Engine, quite interesting choice, by the way. And Amazon, Microsoft have their own. Not all of them have direct access to the Earth observation data, to satellite images. So CrowdIAS and DIASs in general are especially made for that, made to use satellite data and analyze them and process them. Okay, so we will find some interesting information, I hope, there. And the last part, Galileo. So this is European own our own navigation, global navigation satellite system, GNSS. It's interoperable with other huge global navigation systems. We have two of them actually, well, even three. There is a Chinese one actually, but we may talk about two of them. GPS. Actually, we call all of it GPS. It's like it was the first one. So it's normally global navigation system, the global navigation satellite system, GNSS. So GPS is the very name of this very system, but anyway, we call them all GPS. So this GPS, American GPS and Russian GLONASS. So it can cooperate with that. Why is that so important? This cooperation, this interoperability, because normally to localize, to calculate the localization using this systems, we need at least 3 satellites. Normally we have more of them, so that's not a problem normally. But sometimes the signal might be blocked. For example, like in forest, in the city. So that's why we need different systems to increase the number of satellites actually. So this way we can calculate it much better, this localization, than with just only one system. In Galileo we have 26 satellites in constellation. At least early this year it was 26 satellites. 22 of them were operational. Accuracy is not bad. In public, we have 1 meter accuracy, which is not bad, like enough actually for a lot of purposes. And it might be 1 centimeter, but it's encrypted for some military, I suppose, reasons. And applications of Galileo are like huge, not only of Galileo, but of global navigation satellite systems. Like you cannot imagine actually the life now without this, well, let's call it GPS or this GNSS. When we want to go wherever we weren't before, you use it. Okay, you want to car share, you want to take a car share cards or car sharing or something like that. You need this navigation. So it's navigation, but it's also science. It's also some really long list of other examples of other applications. Games, for example, there was this game called Pokemon Go. So you couldn't play it without GPS, of course. And just to the end of our meeting today, the one proposition, the one example of application I like, it's a cryoscan. That's for programming and monitoring the flight routes of unmanned airborne vehicles, UAV. This is a drone here, so we can program its flight route. That's Gdynia, I suppose. That's a town in the north part of Poland. So we can analyze, monitor this flight. First, program it, of course, and that's the application of that. Of course, we need GNSS, Galileo, for example, for that. So, that's self-assessment questions for our last part, and that means, of course, you can find some interesting information here. So that means that we finished for today. That's the end. Yeah, just like 5 minutes, probably too long. So I'm so sorry for that, but I hope you know it's mad at me.
No problem at all. Thank you for
Great.
great class.
It was a pleasure. It would be probably bigger pleasure to be in the place in Portugal.
Yes, of course, it's completely different, but are the
nice
actual
to see you anyway
circumstances.
in those small boxes.
Yes, it is. I don't know if there is more questions. Nobody wrote here in our chat, so I suppose everyone needs to think more about this. It's too much information. So
yes, once again, I strongly encourage you to share your ideas.
Maybe in the next few days.
Yeah, you have time. It doesn't have to be now, but if you want to, you just contact Anna. You have this evaluation form. If you want to contact me directly, not a problem at all. Anna will give you contact to me. So please do it. I'll be happy to help you in any way I can. And with your like feedback, with your information about what is interesting for you, especially, we can prepare the next steps, the next stages of the course of this training, especially for your needs. I hope we will manage. Thank you, Francisca. That's very nice of you.
Okay, thank you also. So I changed to Portuguese time.
Okay.
Ok, thank you. Então, se calhar agora fazemos uma pequena pausa, que foram 2 horas muito intensas. Vamos retomar aqui 5 minutinhos atrasados. Retomamos só aqui ver o tempo, não digo às 1h15, às 4h15, mas 17, que é para dar tempo aqui de absorver isto e passarmos para os próximos tópicos com as professoras Luísa Barci e a professora Cidália Fonte, que já se juntam aqui a nós, que irão falar então da questão do Galileu e também do programa Copernicus. Então retomamos aqui daqui a 4, 5 minutinhos, ok? Obrigada pelo vosso tempo. Até já. Boa tarde,
Então,
novamente.
já está tudo de volta, Ana.
Espero que sim.
Olá, professora Luísa, como está? Tudo bem?
Boa tarde.
Para Cidália também.
Sim.
Obrigado por terem acedido ao nosso convite.
Nada, com muito gosto.
Um gosto, sim.
Prazer em vê-lo também. Espero
Exato.
que estejam todos bem.
Acho que sim, so far, até à data, está tudo tranquilo por aqui.
Ótimo.
Vamos então retomar a sessão. Vamos então começar pela apresentação da professora Luísa Bastos sobre Galileo Prospects and Opportunities. Vai ser em português, portanto esta última parte da sessão. Não sei se a professora tem PowerPoint, se quiser partilhar, penso que já pode.
Vou partilhar a tela então. Já estão a ver?
Sim, exatamente, já estamos a ver.
Pronto, então, boa tarde a todos. E é com muito gosto que aceitei este convite para participar nesta sessão. Eu tenho os meus slides em inglês, para eventualmente, se houver na audiência algum não falante de português, mas falarei em português. Portanto, o tópico da palestra é focado no sistema Galileu, mas antes de falar propriamente das especificidades do sistema Galileu, uma pequena panorâmica dos sistemas de posicionamento por satélite atuais, dos sistemas globais, há outros que são regionais, e do modo de funcionamento e arquitetura muito brevemente. Portanto, nós atualmente temos 4 sistemas praticamente já a entrar em capacidade completa de funcionamento. Para além do GPS e do GLONASS, temos também o sistema chinês e o sistema Galileu, já na fase final de implementação. Todos estes sistemas têm em comum um determinado tipo de arquitetura, em particular são compostos por um segmento espacial, um segmento de controle e um segmento do utilizador. O segmento do utilizador é naturalmente aquele que nos está mais próximo e para conseguirmos obter posições a partir do sistema, temos que receber sinais de pelo menos 4 satélites em simultâneo. Os satélites emitem informação sobre a sua posição e informação também de tempo, e a partir daqui nós podemos calcular as nossas coordenadas, quer estejamos parados ou em movimento em diferentes localizações, terra, mar, ar. Portanto, os sistemas têm enorme potencial. Normalmente designamos estes sistemas por GPS, mas atualmente a designação correta é GNSS, porque GPS é só um deles. O princípio de posicionamento com estes sistemas é muito simples, embora a complexidade toda que está por trás da implementação de um sistema destes, e basicamente baseia-se na determinação das distâncias, como eu referi, aos satélites, distâncias essas que são multiplicadas pela velocidade de propagação do sinal para obter a distância. Os satélites destes sistemas são satélites MEO e estão normalmente na casa dos 20.000 quilómetros acima da superfície terrestre. Para determinarmos essa distância ao satélite, temos que ter em atenção o tempo de propagação e, como naturalmente se percebe, um sinal que se propaga à velocidade da luz necessitamos de ter uma informação muito precisa do tempo para não cometer erros. Só para ter uma ideia, portanto, fazendo umas contas simples, para termos um rigor de 1 milímetro na terminação da distância a estes satélites, que estão a cerca de 20 mil quilómetros, precisaríamos ter medir o tempo com uma precisão de 10 elevado a menos 12 segundos. Habitualmente designamos esta distância que determinamos não por distância, mas por pseudodistância. Porquê? Porque a distância real é difícil de determinar, é mais difícil de determinar, atendendo aos erros que afetam os sinais que são emitidos pelos satélites. E esses erros são de vária natureza, desde logo com origem no próprio satélite, tem origem na parte de hardware e também na própria informação que é divulgada pelo satélite em termos da sua localização, chamadas efemérides dos satélites. Depois os erros associados à propagação do sinal na atmosfera e na ionosfera, e também erros de reflexão no local de observação do sinal. Também muito brevemente, para ter uma ideia de quais são as opções que temos em termos de técnicas de posicionamento com os sistemas globais de posicionamento, nós podemos ter o posicionamento menos preciso, que é aquilo que nós chamamos posicionamento por ponto, PP, e que nos permite obter precisões, de um modo geral, com estes sistemas da ordem de poucos metros até 1 metro, como iremos ver, ou melhor, com o Galileu. Podemos ter um posicionamento relativo que é bastante mais preciso e que é o que permite atualmente maior rigor, que é a obtenção de coordenadas do vetor que liga uma estação de referência de coordenadas bem conhecidas e a estação de observação. Depois, nos últimos anos, tem tido grande desenvolvimento aquilo que se chama o posicionamento PPP, Precise Point Positioning, que implica ter acesso em tempo real a efemérides mais precisas do que as que são difundidas diretamente pelo satélite, portanto temos que ter por outros meios essa informação. O processamento desta informação também implica a utilização de um algoritmo mais elaborado para permitir em tempo real calcular as diferentes perturbações que afetam os sinais e conseguir atingir o objetivo de ter precisões centimétricas. Por outro lado, em qualquer um destas abordagens, nós podemos estar a observar em modo estático ou em modo cinemático, portanto, quando estamos em movimento. Temos então, na parte de estático, o posicionamento PP, que nos permite obter já melhor do que 1 metro, alguns decímetros. O posicionamento diferencial, que nos permite obter até milímetros de precisão, isto dependendo se estamos a usar o código ou a fase dos sinais. A fase é a medida que nos permite obter maior rigor posicional. Quanto ao PPP, permite-nos atualmente atingir centímetros. Em modo cinemático, naturalmente há uma pequena degradação da precisão. Mesmo assim, nomeadamente com o sistema Galileu, conseguem-se precisões posicionais muito, muito boas, de muito boa qualidade, e mesmo também de centímetros em PPP, o que representa um enorme avanço nesta técnica de posicionamento. Centrando-me agora mais então no sistema Galileu, que é o sistema europeu, e ao qual o objetivo desta palestra é dar ênfase. O sistema Galileu começou a ser pensado já há bastante tempo e demorou, enfim, mais de uma década a ser implementado, na verdade, em rigor, cerca de 2 décadas. E o objetivo era ter um sistema independente que não estivesse sobre a alçada militar de outro país e que permitisse uma determinação precisa de posições. Na verdade, foi concebido de modo a ser o sistema civil que permitisse melhor rigor posicional ao utilizador comum e facilitando assim todas as formas de navegação, quer aérea, quer marítima, quer terrestre, já agora quer pedestre. Este sistema, como referi, tem a sua componente espacial, como todos os outros, e a constelação completa estaria previsto ter entre 27 e 30 satélites, distribuídos por 3 planos orbitais, com um semi-eixo maior de cerca de 29 mil quilómetros, e uma excentricidade muito pequena. O período orbital é cerca de 14 horas, o que quer dizer que ao fim de algumas voltas é que o mesmo trajeto é repetido. O primeiro satélite desta fase de implementação do sistema foi lançado em 2011 e atualmente, como disse já o orador anterior, estão 22 satélites em órbita a funcionar, e até ao final do ano, princípio do próximo ano, estará completa a constelação com 24 satélites. Relativamente aos sinais, é uma parte importante a escolha que presidiu à escolha dos sinais Galileu e da sua, digamos, arquitetura, porque eles permitem ter algumas características distintivas dos outros sistemas globais de posicionamento. E, sendo assim, cada satélite permite transmitir diferentes sinais de navegação em frequências da banda L. Todos estes sistemas de navegação por satélite, estes 4 sistemas de que falamos, transmitem sinais nesta banda, portanto é uma banda que, para além disso, é usada também para outras áreas em telecomunicações. É uma banda, digamos, bastante pressionada e que tem que ser protegida. O sistema Galileu emite então vários sinais nestas bandas, designados por E1, E5 e E6, dependendo das frequências, como está aqui indicado. A frequência E1 é uma frequência que propositadamente coincide com frequências dos outros, que são usadas pelos outros sistemas de navegação. Isto tem o objetivo de garantir a interoperabilidade dos sistemas, que foi já referida pelo orador anterior. Temos aqui vários tipos de sinal, então, como eu disse. Em alguns destes sinais são disponibilizados sistemas abertos, e noutros temos sistemas comerciais, portanto há restrições de acesso e são fornecidos por companhias que providenciarão este tipo de serviços. Tem de específico relativamente a outros satélites, a outras constelações, o facto de ter um serviço de segurança de vida, Safety of Life, e também de ter o Public Regulated Service, que tem restrições de acesso e permite a autenticação do sinal, o que, como referirei à frente, é uma vantagem. Para terem então uma perspectiva da distribuição das bandas de transmissão dos diferentes sistemas, dos 4 sistemas Galileu, GPS, GLONASS e Beidou, ou Compass, tenho aqui representado esse espectro e as diferentes frequências de transmissão, que, como referi, são comuns. Por exemplo, o L1 é comum ao sistema Galileu e ao sistema GPS, foi intencional, e é partilhado também pelos outros sistemas de posicionamento. Por outro lado, Na concepção do sinal foi utilizado um tipo de modulação que tem algumas vantagens relativamente à modulação utilizada pelos satélites do sistema GPS, que é vantajoso, nomeadamente no caso de interferências. Portanto, estes sinais são mais imunes a interferências. Também tem maior potência, o que em ambientes, nomeadamente urbanos ou florestais, tem também essa vantagem de não ser tão atenuado, portanto, ser mais fácil de aceder. O sinal E6 do sistema Galileu também coincide com um sinal L3 a ser implementado nos novos satélites do sistema GLONASS, portanto, novo para melhorar a interoperabilidade. Portanto, o tipo de sistemas que o Galileu providencia classificam-se no acesso livre, comercial, safety of life e public regulated. No que respeita às características específicas do Galileu que lhe conferem vantagens competitivas sobre os outros sistemas, sublinho então a possibilidade de autenticação do sinal. Isto quer dizer nós termos a certeza que o sinal que estamos a receber é de um satélite Galileu. Portanto, o serviço Public Regulated Service, que será destinado fundamentalmente a forças militarizadas e de segurança, a integridade da mensagem e o TER é o único sistema neste momento que permite ter o serviço Search and Rescue. Isto quer dizer que, contrariamente aos outros sistemas em que não há comunicação do observador para os satélites, para a componente espacial do sistema, neste caso há a possibilidade de ser enviada uma mensagem de alerta em caso de acidente em qualquer ponto do globo. O sistema Galileu começou a providenciar serviços em dezembro de 2016, ainda não com a constelação completa, mas já providenciando resultados de posicionamento com alguma qualidade. Em 2018 foi decidido ter um sistema de livre acesso de elevada precisão, o chamado High Accuracy Services, e esta decisão permite ao GPS ser o sistema GNSS que permite ao cidadão comum obter maior rigor posicional sem ter que subscrever um serviço. Como já referi, as outras vantagens são o facto de ter o serviço de Search and Rescue e de os sinais terem melhor desempenho em ambientes problemáticos. E estes ambientes problemáticos podem ser, como já referi, ambientes urbanos, ou ambientes em que haja bastante vegetação, por exemplo. Os sinais GPS têm revelado ter, de um modo geral, um desempenho, nesta fase pelo menos, um desempenho melhor do que os sinais que atualmente podemos utilizar do sistema GPS. Esta possibilidade de utilizar este High Accuracy Service livremente como eu referi, foi uma decisão recente. Para isso, torna-se necessário que seja fornecida informação mais rigorosa sobre os relógios a bordo dos satélites, o estado dos relógios, sobre as órbitas e sobre as perturbações atmosféricas, nomeadamente as correções ionosféricas. O chamado Signal in Space Error, que dá uma ideia da qualidade que podemos esperar da determinação da posição, excedeu as expectativas e ronda os 25 centímetros, o que significa que tem um desempenho melhor do que o do sistema GPS. Isto permite, a nível global, portanto, a qualquer utilizador, poder alcançar precisões da ordem dos 20 centímetros na componente horizontal e dos 40 centímetros na componente vertical. Portanto, estamos a falar do posicionamento PP, se recordam do slide atrás, é o que tem menos rigor e, mesmo assim, este serviço, High Accuracy Service, permite obter precisões muito elevadas. E, como referi, o Galileu será a primeira constelação a fornecer este tipo de serviço. Uma outra vantagem ligada à concepção dos sinais e à arquitetura do sistema é o facto de ele permitir um desempenho muito elevado na utilização de smartphones. Isto, como vamos ver, é algo que tem muito impacto, nomeadamente a nível empresarial, para o potencial de exploração é enorme. Portanto, os sinais GPS, ao terem canais chamados dateless, portanto, sem dados, dedicados, permitem ter ganhos de processamento quando utilizamos os processadores internos dos smartphones, que estão, obviamente, limitados pelo oscilador interno, mas também a nível dessas componentes, dos relógios, dos sistemas miniaturizados, tem havido grandes desenvolvimentos e, portanto, o que devemos esperar é melhorias significativas a breve prazo. E naturalmente que a possibilidade de confirmar aos utilizadores que estão a receber sinais de um satélite de Galileu e não um sinal, digamos, de spoofing ou de um sinal intencionalmente errado para interferir com os resultados, é de facto uma enorme vantagem, atendendo a que o problema das interferências é neste momento uma preocupação enorme para este tipo de tecnologias de posicionamento. A nível daquilo que foi a definição, do que foi a definição dos objetivos do sistema GPS de Galileu para determinação da distância ao satélite, determinação da posição e rigor na determinação de tempo, o sistema correspondeu e excedeu até as expectativas. O que quer dizer que o Galileu tem, de facto, potencial para dar resposta a aplicações exigentes. Dentro do tipo de aplicações GNSS, podemos classificá-las em classes, em que temos a primeira, a determinação de posição, portanto, aplicações de localização. A segunda, a navegação, que nos importa não só saber a posição, mas como chegar ao nosso destino. A monitorização, que é algo que tem interesse naturalmente na gestão de tráfego, na gestão de frotas e, enfim, em logística, etc. portanto, essa aplicação de monitorização do movimento, sejam pessoas, animais, mercadorias, o que seja. Depois, naturalmente, a aplicação na produção cartográfica e a aplicação na determinação do tempo, com implicações em muitas áreas, nomeadamente na gestão de infraestruturas críticas. Aqui mostro alguns resultados obtidos aqui no Porto, no Observatório Astronómico, de posicionamento só usando os sinais do sistema Galileu. Aqui estou a mostrar intencionalmente o resultado do posicionamento em 2017, e digo intencionalmente porque nesta altura o sistema ainda não tinha menos de 20 satélites, portanto uns 16, e mesmo assim, como podem verificar, o posicionamento só Galileu permite obter valores muito comparáveis ao sistema GPS, quando não melhores. Relativamente à questão do posicionamento, e porque estamos a falar para empresas, eu vou-me focar no posicionamento usando smartphones. E porquê? Porque isto representa de facto uma mudança de paradigma. Há poucos anos atrás, para obtermos precisões centimétricas, nós necessitávamos de ter receptores geodésicos que custavam alguns milhares de euros. Atualmente nós conseguimos obter precisões idênticas usando o nosso smartphone. E portanto isto quer dizer de facto que o posicionamento de precisão chegou ao mercado de massas. E com a possibilidade de integrar com outras tecnologias e outros sistemas de posicionamento, isto representa um potencial enorme, de facto. Porquê é que isto foi possível? Porque em 2016 a Google introduziu o Android 7, que permite o acesso a dados brutos dos smartphones, e em 2018 entraram os primeiros smartphones com receptores de 2 frequências e já, portanto, permitindo o acesso aos sinais Galileu e GPS em 2 frequências. Isto desde logo nos questiona se o smartphone não será, e provavelmente será, a próxima geração para os sistemas de informação geográfica. Temos já atualmente milhões de smartphones a serem utilizados com esta capacidade. Então, começando pelo posicionamento estático com smartphones, aquilo que eu mostro aqui é o resultado da utilização de um smartphone Xiaomi, um Mi 8, e aqui podem ver o bom desempenho, quer nas componentes horizontais, quer na componente vertical. Isto também é possível, naturalmente, porque a partir dos desenvolvimentos no Android 7, há vários software de acesso livre para a gestão destes sinais, destas medidas. Para além do posicionamento estático, fizemos também experiências em modo cinemático e, portanto, aquilo que se chama navegação geodésica significa a determinação da posição de uma plataforma para fins de posicionar sensores que estão a bordo dessa plataforma. Podem ser câmaras ou podem ser outros sensores, pode ser um lidar, enfim, podem ser vários outros equipamentos. E aqui chamar a atenção que o custo dos smartphones está nas centenas de euros, muito diferente do custo dos receptores geodésicos de multifrequência, que custam ainda uns milhares de euros. E aqui podemos ver então os 2 tipos de smartphones que estávamos a utilizar. Neste caso estávamos a utilizar também um Huawei P10, no caso do Xiaomi, estamos a compará-lo com um receptor geodésico Novatel e podemos ver que o desempenho é a nível do decímetro, o que é de facto muito bom. Fizemos alguns testes também a nível de utilização do smartphone numa aeronave. e temos aqui alguns resultados, naturalmente agora não, o rigor não tão elevado, mas ainda assim muito bom para os equipamentos que estamos a usar, em que eu chamo a atenção que aqui isto significa, DF significa que é o posicionamento relativo, significa que estávamos a usar uma estação de referência para obter a solução final, e o SPP é o PP, portanto é o posicionamento menos preciso. Portanto, nos testes que fizemos, temos um bom desempenho, atendendo aos meios utilizados e aos custos. Portanto, aqui temos navegação terrestre, aqui numa autoestrada, temos alguns pormenores em que podem ver o bom resultado obtido com o smartphone, e aqui em meio aéreo. De referir também agora outros tipos de utilizações dos sinais GNSS. Neste caso, nós estivemos a utilizar aquilo que chamamos os sinais diretos, e que nos permitem então fazer o posicionamento e navegação por satélite, mas estes sistemas dão a possibilidade também de explorarmos os sinais refletidos ou refratados e termos outro tipo de informação, sendo que estamos a usar, neste caso, os sinais GNSS como uma ferramenta de detecção remota. Existem já sistemas a obter informação sobre correntes, por exemplo, este sistema Cyclone Global Navigation System, e ventos. Neste caso foi mesmo um sistema implementado para monitorização de ciclones nos Estados Unidos. Portanto, é uma forma de detecção remota usando os sinais GNSS. Mas a capacidade de posicionamento do sistema GNSS é por si só também um motor para o desenvolvimento de aplicações de detecção remota mais precisas, e, portanto, existe um potencial elevado para desenvolvimento do mercado de observação da Terra, e dado que qualquer tipo de plataforma, esteja no espaço, no ar, no mar, beneficia da determinação precisa de posições. E o GPS pode, portanto, potenciar diferentes métodos de observação. Naturalmente, temos diferentes métodos de observação a diferentes escalas temporais e espaciais, com diferentes plataformas para a monitorização da Terra. Portanto, isto permite grandes desenvolvimentos. E também, como sabemos, e já foi referido, o GNSS tem impactos e benefícios em muitas áreas de atividade, desde logo a geomática, que é a minha área, a dinâmica terrestre, os serviços LBS, que estão em franca explosão, a agricultura, enfim, a logística, fundamental nas cidades inteligentes, e também na parte de navegação, em aplicações específicas de automatização, de gestão de tráfego, enfim, portagens automáticas, etc. E também não podia deixar de referir a utilização do GPS para avaliar o impacto do vírus que agora nos assola, e este dá uma imagem do antes e o depois do tráfego aéreo em março e em abril. Mas temos então muitas possibilidades pela frente para explorar os smartphones, porque os smartphones não têm só os sistemas GNSS, têm outros sensores como acelerómetros, como câmaras, e giroscópios, etc., que nos permitem ter um verdadeiro sistema de posicionamento e orientação. A partir da exploração destes aspectos, foram desenvolvidos alguns projetos, de que dou aqui só uma breve referência, em várias áreas, desde a partilha de meios de transporte urbano até a utilização de próprios sinais refletidos para análise, para estudos florestais e, enfim, outros. Portanto, o que é que nós temos atualmente ao nosso dispor? Temos, para além do sistema GNSS, muitas plataformas de detecção remota, incluindo os novos satélites, nanosatélites e microsatélites. Temos também atualmente uma capacidade computacional extremamente potente. Temos a aparecer as novas tecnologias de comunicação 5G que vão trazer, configuram uma revolução nesta área. Temos a internet das coisas e as tecnologias MEMS e os smartphones. Portanto, temos aqui um conjunto enorme de oportunidades para implementar novos sistemas de monitorização de baixo custo e elevada precisão e novos serviços baseados nestes dispositivos que estão disponíveis no mercado de massas e que nos permitem dar um conjunto enorme de informação ao cidadão comum. Portanto, as constelações de nanosatélites estão em franco desenvolvimento, como eu disse, estão, digamos, na infância. Isto vai-se assistir agora a uma explosão deste tipo de plataformas e à sua exploração, naturalmente, que permite desenvolver novos serviços. Também o mercado dos drones beneficia imenso destes desenvolvimentos com o sistema Galileu e deste potencial de elevada precisão do sistema Galileu. E, por outro lado, até o próprio setor do espaço, quer a navegação, quer a gestão de detritos no espaço, que é um problema que nos confrontamos atualmente, tem também possibilidade de exploração destes sistemas e beneficiam da capacidade, nomeadamente, do sistema Galileu. Mas nem tudo são facilidades e, como eu referia atrás, neste momento temos um problema sério, que é o problema das interferências, muitas delas intencionais, e que podem criar graves dificuldades e questões de segurança nos sistemas ligados com segurança de vida e também nos sistemas militares. Neste aspecto, como eu referi, o sistema Galileu, pelo facto de permitir a autenticação do sinal, tem aqui uma vantagem sobre os outros em termos de minimizar os impactos destas interferências. E este é mesmo um dos desafios maiores atualmente, é providenciar uma navegação de segurança. Neste mundo em mudança, é de facto de ter grandes expectativas naquilo que poderá ser o desenvolvimento de novas aplicações, sabendo nós que a sociedade hoje em dia cada vez mais exige a informação em tempo real, na palma da mão. Por isso não é de estranhar que as previsões de desenvolvimento do mercado sejam enormes, sendo que o mercado das soluções LBS, dos Location Based Service, e do tráfego, do transporte, constituem a maior fatia deste negócio. E com isto termino, desde já com um incentivo ao aproveitamento da oportunidade que o Galileu dá para desenvolvimento de novos negócios e de novas aplicações. Muito obrigada. Peço desculpa porque demorei mais uns minutos do que ao que devia.
Foram só uns minutos, isto também já vinha um pouquinho atrasado, acho que não há assim grande problema. Pedia que deixássemos as questões todas para o final, mas se quiserem ir colocando aqui no nosso chat, por favor, alguma dúvida. Como vocês já sabem, também já disse isto no início da sessão e de manhã, as professoras estão disponíveis depois para vos responder a mais algumas questões mais técnicas, mais específicas, que vocês queiram, até se quiserem marcar pequenas reuniões, desde que as pessoas tenham um horário, consigamos encontrar aqui um horário comum, será possível. É só mandarem um e-mail ou para mim, as empresas estão no caso no Vote Space sabem, ou para o nosso e-mail space@ipn.pt e tentamos fazer aqui esse ajuste e essa marcação desses encontros. Passamos então à nossa última apresentação da tarde. O dia já vai longo, mas não é um tema menos interessante que os outros, pelo contrário. Vamos então ver aqui a questão do programa Copernicus com a professora Cidália. Eu já apresentei a professora, se calhar não se tinha juntado mais, mas já foi aqui apresentada. A professora aqui da Universidade de Coimbra. Não sei se quer partilhar o ecrã.
Não consigo partilhar porque está partilhado. Acho que é da
deve ser a professora Luísa.
Agora já devo conseguir. Exatamente.
Peço desculpa.
Tem mal. Já estão a ver a minha tela?
Já estamos a ver, exatamente, sim. Quando quiser, então.
Ok, eu vou falar um bocadinho sobre observação da Terra, observação e monitorização da Terra e, em particular, do programa Copernicus e das missões Sentinela. O primeiro palestrante já falou muito sobre algumas destas questões, portanto vou no início começar por, enfim, apresentar um bocadinho estas questões novas que aparecem, que são a observação da Terra e a Terra digital. E as oportunidades que vêm com estes novos conceitos. Depois o programa Copernicus, as missões Sentinela e depois, no fundo, para que é que estes dados podem ser usados, embora também já se tenha falado nisso, e no final umas pequenas conclusões. Ok, então a observação da Terra tem como objetivo, no fundo, agregar ou recolher e agregar informação acerca dos fenómenos físicos que ocorrem sobre a Terra, biológicos, químicos, etc. Portanto, é um sistema de observação da Terra que normalmente está assente em observações remotas e, portanto, em detecção remota. Áreas de aplicação, basicamente, é só uma questão de imaginação. Toda a informação quase que é georreferenciada. Muitos fenómenos podem ser observados remotamente, a partir de satélites e plataformas aéreas, etc. Portanto, estão aqui alguns exemplos: recursos naturais, transportes, clima, a gestão da alimentação, agricultura, etc., emergências, doenças, enfim. Este conceito de terra digital, já agora eu estou a falar em português, enfim, podia ter falado em inglês, eu fiz os slides em inglês, e portanto depois também se houver alguém...
Vamos manter o evento em português, estava também planeado, para as nossas empresas, penso que neste momento já nem sequer temos aqui ninguém estrangeiro, só estão portugueses, portanto...
Pronto, ok. Mas de qualquer forma os slides estão em inglês.
Exatamente.
Portanto, a terra digital é um conceito que começa agora a surgir. O objetivo, no fundo, é ter um modelo digital da Terra, que pode ser usado para a sua gestão. Portanto, isto requer dados, requer criação de modelos e depois requer a tecnologia toda, que envolve a recolha de dados, o processamento, a disponibilização. Portanto, temos aqui sensores físicos, temos os cidadãos que começam a ser uma importante fonte de dados, até no seguimento do que a doutora Luísa Bastos disse. Com as capacidades que os smartphones neste momento têm, os cidadãos têm que começar a ser encarados como uma importante fonte de dados, porque têm sensores na sua mão constantemente, com localização, com câmaras, e portanto são uma fonte importante de informação. Claro, depois temos Big Data, temos a inteligência artificial que tem que estar no fundo associada a isto tudo. Portanto, são conceitos novos que estão a começar a surgir e que naturalmente trazem imensas oportunidades. Ok, então agora mais concretamente sobre o programa Copernicus. O primeiro palestrante já falou bastante sobre o assunto. É um programa europeu que tem como objetivo a observação da Terra. Tem disponíveis dados, tanto recolha de dados e serviços, que estão baseados em recolha de informação a partir de satélites, mas também em sensores terrestres. e toda a informação é livre, é de acesso livre e aberta, e, portanto pode ser acedida em qualquer cidadão, mesmo fora da Europa. Portanto, o programa Copernicus tem estes 6 serviços principais, que são a atmosfera, a parte marítima, land, portanto, alterações climáticas, segurança e emergência. Eu vou passar rapidamente, enfim, uma pequena visão deles todos e depois vou-me dedicar um bocadinho mais sobre o land. Portanto, estes serviços associados à parte da atmosfera pretendem monitorizar a qualidade do ar, a camada de ozono, as emissões para a atmosfera, radiação solar, etc. Portanto, tem dados e tem serviços disponíveis. A parte do climate change, enfim, fala-se por si própria, é compreensível. Portanto, informação sobre o clima passado, presente e modelação do futuro. Depois, a parte da segurança, para a gestão de crises e estar preparado para, no caso, surgir alguma crise. Tem informação relacionada com vigilância marítima, com fronteiras e, no fundo, assistência a países terceiros, no caso de ocorrer alguma crise ou uma emergência. Pronto, depois a parte da emergência está relacionado principalmente com inundações, fogos florestais e secas. Portanto, tem dados e tem produtos também disponíveis que podem ser obtidos e feito o seu download. A parte marítima também tem serviços e produtos para a segurança, para a gestão de recursos marinhos, e da parte da gestão ambiental costeira e marítima, e a parte de clima e meteorologia. Agora, o LAND tem como objetivo fazer a análise dos parâmetros biofísicos e gerir ou gerar mapas de cobertura e uso do solo, identificar os chamados hotspots, portanto locais onde há variáveis que são importantes e que têm que ser monitorizadas, e tem imagens e dados de referência que podem ser usados, por exemplo, para validar mapas. Então vamos olhar um bocadinho em detalhe mais para o que está disponível no LAND. Eu não vou falar sobre o Global e o Pan-European, portanto são dados, o Global são dados para o planeta inteiro, eventualmente para empresas terá talvez menos interesse, mas de qualquer forma podem depois explorar com mais detalhe. Os Pan-European, portanto, são usados para a Europa e países vizinhos. O Local é a informação mais local e com mais detalhe que eventualmente pode ser mais útil. Então o Local tem estes 4...
Desculpa, professora, mas está no primeiro slide intencionalmente ou somos nós que estamos aqui?
A sério? Então eu estou a passar os slides. Eu estou a ver
ok, então
slides.
eu não sabia, depois parecia-me que a professora estava a falar de alguma coisa que devíamos estar a ver e acho que estamos aqui.
Então não estão a ver, então esperem só um momento que eu vou parar.
É melhor sair e voltar. Peço desculpa.
Ora, essa. Então,
ok, agora já estamos no outro slide. Agora estamos no sumário.
A sério. Bem, então vou partilhar outra vez. Ok. Se calhar é porque eu mudei de ecrã. Ou seja, eu vou mostrar no ecrã.
Exatamente, devia estar a passar num ecrã e a partilhar no outro.
Esqueceu-se do que é que era suposto estar a ver. Pronto, então fica no ecrã inicial. Ok, então vou passar os slides rapidamente do que já falei, ok? Portanto, a observação da Terra. Já vem agora os slides a passar.
Agora estamos a ver, não estamos em modo de apresentação, estamos no slide do sumário, mas não em modo de apresentação sequer.
Isso não está a passar?
Não, e até vemos as notas e tudo o que tem.
Mas eu não vejo nada disso. Ok, então só um momento.
Deve ter a ver com os ecrãs.
Desculpem lá, isto não me tem acontecido. Vamos fazer de outra maneira. Vou interromper o compartilhamento outra vez, desculpem lá, que é para eu ver o que é que está aqui a passar. Isto realmente não está... Ok. Então, vamos... Eu acho que o problema foi o PowerPoint que foi-se abaixo. Desculpem lá, tenho que reiniciar o PowerPoint. Ora...
Ok, agora estamos em modo de apresentação na capa.
Estão a ver a passar.
Exatamente, sumário, exatamente.
Pronto. Então, observação da Terra, áreas de aplicação, a Terra digital, o programa Copernicus e, portanto, estas 6 áreas de aplicação, estão a ver? Então,
sim, estamos.
E a atmosfera, clima, segurança, emergência, parte marinha e a parte do land. E então ia falar um bocadinho, portanto temos aqui o global, o pan-European e o local. Na parte do local temos estas 4, no fundo, conjuntos de dados disponíveis, isto já é informação, já nem são dados. Portanto temos o Urban Atlas, não sei se é do conhecimento geral. O Urban Atlas tem já várias versões disponíveis e toda esta informação está disponível, que são produtos adicionais criados no âmbito do programa Copernicus, que estão disponíveis para download e usar em qualquer análise. O Urban Atlas é um produto que está disponível para as zonas da Europa com mais do que 100 mil habitantes. Está aqui neste mapa em baixo as zonas para onde está disponível, portanto em Coimbra é uma das zonas incluídas, mas não cobre o país inteiro. Portanto é um mapa de coberturas de solo com classes portanto, muito detalhadas e está aqui um exemplo para a zona de Coimbra. Tem esta limitação de não estar disponível para o país inteiro, no entanto há a informação portuguesa, a Direção-Geral do Território, que tem alguma semelhança com a informação do Urban Atlas. Depois, eu não vou passar a todos, achei que este do Building Height, que é a altura dos edifícios, pode ser interessante. Está disponível há pouco tempo no programa Copernicus informação sobre a altura dos edifícios em cidades da Europa. Está aqui um exemplo, Portugal só está para a zona de Lisboa, portanto, informação sobre a altura dos edifícios em várias zonas da cidade. Depois, portanto, as zonas ribeirinhas, existe informação detalhada também, está disponível para a Europa toda. É um mapa também de cobertura e uso de solo, com informação detalhada ao longo de todas as zonas ribeirinhas, não é? Portanto, todas as linhas de água. E está disponível em vários níveis, portanto, aqui está uma nomenclatura mais geral e depois, quando vamos ao detalhe, tem uma nomenclatura muito mais detalhada. Não se vê aqui a nomenclatura toda, portanto, aquilo depois tem muitas classes, muitas dezenas de classes. Na parte das zonas costeiras, também está disponível para a Europa toda, mapa de cobertura e uso do solo, para as zonas todas costeiras portanto, da Europa, com grande detalhe também. Portanto, tudo isto são dados que estão disponíveis para fazer download e podem ser utilizados por qualquer pessoa. Depois, temos a parte de imagens e dados de referência. O que é que são estes dados de referência? Dados de referência, no fundo, são dados que são utilizados para validar mapas. Toda esta informação precisa, muitas vezes, de dados que são recolhidos localmente. Portanto, os chamados in situ data. E, portanto, aqui está disponível alguma informação, já lá vamos, portanto vamos aqui primeiro ver a parte do modelo digital terreno. Também está disponível um modelo digital terreno para a Europa inteira. Foi criado a partir do SRTM e do ASTA, portanto são modelos americanos, mas portanto, este para a Europa foi criado a partir desses, os outros são globais, portanto todos mesmos para todo lado, mas portanto, tem 25 metros de resolução e tem um erro médio quadrático de mais ou menos 7 metros. Portanto, está disponível, é só fazer download. Depois tem a parte de hidrológica, tem a rede hidrológica para a Europa toda também, disponível, só fazer download e já tem informação até mais completa sobre as linhas de água. Aqui então, o Lucas são dados de referência, são dados recolhidos in situ na Europa, com um protocolo muito estrito, envolve fotografias em locais pré-definidos e recolha sobre qual é a informação de cobertura e uso de solo. Depois temos, por exemplo, imagens de muito alta resolução, que também estão disponíveis, mas como serviços WMS. Portanto, não é possível fazer download, mas eles podem ser visualizados no sistema de informação geográfica, por exemplo, até para criar dados de referência, para digitalizar fenómenos que sejam visíveis nas imagens. Relativamente às missões Sentinel, portanto, também já foi falado pelo palestrante que falou a seguir ao almoço. Portanto, a missão Sentinel tem 6 missões, no fundo, de 1 a 6, lançada pela ESA. Os satélites, portanto, das missões Sentinel-1, portanto, recolhe dados radar e para serviços de terra e do oceano. Sentinel-2 são imagens ópticas para observação da Terra. Depois o 3 tem imagens ópticas, radar portanto, dados altimétricos de alta resolução. 4 é mais para a monitorização, ou vai ser, porque ainda não está a funcionar. Monitorização da atmosfera e da qualidade do ar. O 5 também para a atmosfera. E o 6 que acabou de ser lançado este mês, não, que já estamos em dezembro, mas no mês passado. Ora bem, o Sentinel-1 disponibiliza dados radar para serviços de terra e oceano, tem 2 satélites, o 1A e o 1B. Está aqui uma lista de produtos e de modo de aquisição de dados. Portanto, estes dados radar têm vários modos de aquisição, são disponíveis os produtos em 3 níveis de produtos. O processamento radar é um processamento com alguma complexidade, portanto tem dados sobre a amplitude e sobre a fase. Por exemplo, estes produtos aqui, o SLC, que já o palestrante a seguir ao almoço falou, o Single Look Complex, permite ter informação sobre a fase, que nos permite tirar, então, obter dados que permitem detectar deformações e pequenos deslocamentos. Depois o Sentinel-2 recolhe imagens ópticas, também com 2 satélites, portanto o A e o B, portanto são os chamados satélites gêmeos, que permitem conjuntamente aumentar a resolução temporal, ou seja, o tempo de revisita do local, que em vez de ser 12 dias, portanto se fosse só um satélite, ou neste caso 10 dias, que é o Sentinel-2, ser 5 dias no Equador. Este Sentinel-2 tem a bordo um sensor que recolhe dados em 13 bandas, tem resoluções espaciais de 10, 20 e 60 metros e, portanto, está aqui informação sobre as várias bandas. Portanto, tem estas bandas no visível, verde, vermelho e azul e depois em infravermelho, e depois tem aqui estas bandas na parte do infravermelho que permitem obter mais detalhe na vegetação. Pronto, depois tem ainda mais algumas bandas de 60 metros, são mais para correções atmosféricas, e tem aqui as bandas 11 e 12 para neve, gelo e alguns tipos de vegetação. Os produtos que estão disponíveis pelo Sentinel-2, portanto temos 3 níveis. As imagens que estão disponíveis com este nível 2A já têm correções atmosféricas, já têm correções geométricas e, portanto, estão prontas a utilizar. São disponibilizadas em faixa, portanto, por 100 quadrados, no fundo, de 100 metros quadrados, desculpem, 100 km quadrados e cada imagem tem aproximadamente 800 megabytes. O Sentinel-3 portanto, recolhe informação óptica, radar e altimetria para fins marinhos e terrestres e, por exemplo, para analisar a topografia da superfície do oceano e a temperatura, a cor do oceano. Portanto, são mais oceanográficos e meteorológicos. Os produtos do Sentinel-3, portanto, também têm vários níveis de produtos e muitos produtos associados com a atmosfera, o oceano, portanto não há tempo para ir em detalhe relativamente a eles todos. O Sentinel-4 pretende depois, quando estiver disponível, dar informação sobre a qualidade do ar. E agora como aceder a estes dados todos? Portanto, já se falou no DIAS, que permite não só recolher, portanto, ter acesso aos dados, mas ter serviços para os processar. Existe também o Open Hub, que permite a qualquer pessoa fazer download, desde que se registre na plataforma, fazer download de dados. E temos uma API que permite integrar em programas que se façam, scripts, o download automático das imagens, que permitam automatizar processos, que é muito importante nos dias de hoje. Isto é um exemplo do Open Hub, onde, de acordo com uma sequência no fundo, um inquérito, que nós dizemos que se queremos imagens de Sentinel 1 ou 2 ou 3, as datas e da zona onde queremos, e depois vem-nos uma lista de informação que está disponível e é só fazer download. Agora, para que é que estes serviços podem ser utilizados? Ok, então o que está disponível no Copernicus, temos modelos digitais de terrenos, temos mapas de cobertura e uso de solo, que são, a maior parte deles, produtos estáticos. Portanto, alguns deles não são, como por exemplo a altura dos edifícios, não está disponível facilmente noutros locais, mas são produtos que têm alguma limitação na sua utilização, no sentido de que são produtos estáticos, podem servir para apoiar outro tipo de análises. No entanto, a utilização de imagens de satélite que aparecem, ou melhor, temos imagens novas de 5 em 5 dias ou de 6 em 6 dias, dependendo dos sistemas, permite uma infinidade de aplicações. É preciso, sim, desenvolver métodos, de preferência automáticos, para tratar toda essa informação e podem ser utilizados para monitorização e detecção de alterações, que é uma área muito importante que começa a surgir, porque nós não queremos informação estática, o que nós queremos é informação ao longo do tempo. E para ter informação ao longo do tempo, temos que ter séries temporais de dados para analisar e detectar alterações. Aplicações. As aplicações são imensas, porque quase tudo é visível a partir das imagens de satélite, juntando radar, juntando a parte óptica. Temos aplicações na agricultura, no ambiente, até no cadastro, detecção de formações, gestão florestal, detecção de alterações, qualidade da água, emergências, recursos naturais, gestão das zonas urbanas. Portanto, as aplicações são imensas. O que é necessário? Eu diria que a principal coisa que é necessária são competências na área. Ou seja, competências na área dos sistemas de informação geográfica e Geographic Information Science, porque este GIS, o S, vem já de Science e não de Systems, porque digamos que esta área se desenvolveu muito e já é considerada uma ciência. Competências no processamento, já na recolha dos dados geoespaciais, no seu processamento, na integração de dados, que cada vez é mais importante, porque os dados disponíveis são terabytes de dados por dia. Portanto, temos aqui Big Data também, processamento em tempo real. Depois é preciso ter uma componente importante de validação, porque a quantidade de dados é muito grande, podemos fazer muitas coisas com elas, mas é preciso ter a certeza que os resultados são de qualidade e, portanto, é preciso validar. Classificação, claro, está aqui envolvida a inteligência artificial também. Claro, é preciso hardware e software, mas isso nos dias de hoje acaba por já ser menos importante, porque existem já serviços na web E, enfim, a evolução tecnológica na parte do hardware é muito grande. Na parte do software, existe também muito software livre, de utilização livre, que pode ser usado se não se pretender utilizar software proprietário, que tem custos muito elevados, embora, claro, às vezes tenham umas capacidades maiores. Enfim, a jeito de conclusões, quantidades enormes de dados disponíveis, é preciso boas ideias para os utilizar. E, claro, os desafios são muitos. E é preciso, então, no fundo, tentar obter alguma inovação na utilização destes produtos para que eles efetivamente sejam possíveis de aplicar em novas áreas e em novas ideias. E pronto, era isto que eu tinha para apresentar.
Obrigada, professora Cidália, mais uma apresentação aqui sobre esta temática. Não sei então se há questões das nossas, temos aqui presente algumas startups do Workspace e empreendedores que estão aqui numa fase embrionária a começar. Não sei se há questões ou daqui dos nossos colegas.
Eu tinha uma questão.
Força, se calhar vamos então vamos deixar aqui o chat de lado e vamos passar a fazer, já estamos aqui há tantas horas, vamos falar aqui um pouco.
Ok, boa tarde. A minha questão era para a professora Luísa Bastos, tem a ver com o sistema GNSS, neste caso. Queria perceber um pouco melhor como é que funciona essa novidade do Galileu em termos de precisão, se isso tem alguma coisa ainda a ver com aquele sistema de precisão aumentada que era o SBAS, se é um sistema desse tipo, e se está previsto no futuro também um serviço de correção diferencial para os receptores de telemóvel. Como falou nestes sistemas agora mais modernos que funcionam com o telemóvel, se também está prevista essa situação para o serviço móvel.
Obrigada pela sua questão. Os resultados que eu apresentei e a indicação que eu dei de precisão não envolvem os chamados SBAs, os sistemas de aumento. De facto, aqui na Europa temos o sistema EGNOS, e que continua a ser melhorado e desenvolvido, e que é muito utilizado, em particular, na parte da aviação comercial. Mas este serviço de elevada precisão não passa pelo uso necessariamente do SBAS. Claro que os sistemas de aumento são sempre úteis, nomeadamente em ambientes urbanos, etc., em que pode não ser tão fácil ter um número suficiente de satélites para obter a precisão desejada. A outra questão que me estava a colocar, a resposta é sim, está a ser pensada uma difusão de correções para telemóveis destes sistemas SBAS.
Ok, obrigado.
Nada.
Acho que é uma boa notícia para as empresas que podem aqui poupar um pouco em equipamento se houver essa correção com dispositivos que são mais económicos. Não sei se há mais questões.
Claro, agora só um comentário. Os resultados que eu apresentei de testes que fizemos aqui, tenho que sublinhar que são resultados de processamento posterior e, portanto, no caso de se querer tempo real, necessitamos ainda de alguma capacidade instalada no smartphone para poder processar em tempo real. Ou então, se não precisarmos de tanto rigor, podemos recorrer em tempo real aos SBAs para melhorar a precisão. Mas a capacidade de cálculo também está a aumentar, a própria capacidade de processamento dos sistemas nos smartphones, e, portanto, acho que o futuro é promissor.
Já agora, só mais uma pergunta. Já que abordou essa questão do pós-processamento, não sei se fizeram a seguinte experiência, utilizando um smartphone ou utilizando um receptor geodésico, portanto ligado em modo nativo, sem correções absolutamente nenhumas da RNEP, por exemplo, as precisões são semelhantes ou se há diferenças, ainda assim?
Nós utilizamos de facto um receptor geodésico sempre, tivemos sempre e também fizemos alguns testes do que é que dava o resultado, aquilo que me está a perguntar, creio que é as posições que se obtêm na mensagem de meia do
Sim, em modo absoluto, sim.
A qualidade é idêntica. Agora, há aqui uma questão que ainda precisa de desenvolvimento nos smartphones, que a antena é muito mais fraca. Portanto, se não tivermos em boas condições de recepção, de facto há muitas falhas e a qualidade do sinal é pior do que no receptor geodésico. Mas isso está relacionado essencialmente com a antena. Isso também é um aspecto que se calhar se vai alterar em breve, com a possibilidade de ter uma antena externa no telemóvel.
Ok, obrigado.
May I ask question in English, because my Portuguese
is
still so poor, so I can follow your presentations only thanks to that the slides were in English. But anyway, so I would like to point out that I feel that the changing of the paradigm of measuring device from professional and specialized ones to platforms and applications available on the smartphone is something very important, because it literally puts in your pocket, directly in your pocket, the ability to create the applications you need following this real-time challenge and also earn money on it. However, I think that we should work on reducing the risk of a mistake, which was made in public education in general, public as well, in the process of popularizing access to information. So we had thousands of TV channels, the internet access, broadband, and search engines, and all this stuff. So my point is that we need to focus on two areas. The first is to teach the criteria for evaluating and selecting the right information and also data for the purpose for which they are collected, parallel to the process of the sophisticated process of the acquisition, the processing and sharing. And why? Because a new technique always seems to be more reliable, so people are using it less critically, and that can be dangerous. So the examples are, well, 100 years old. So you can definitely you can remember this Orson Welles audio broadcast. The Martians are attacking. So the millions of people in the USA in 30s just ran away from their homes. And it's repeated many times as along the new technology was implemented. So I think the showing that the data could not especially be so accurate, and showing that the satellite missions are intended to specific reasons, and how to select the set of satellites and then set of data and the way of processing them in parallel of the technical ability of providing those data should be very important, because people who are not aware with the technology could mix up it very easily. And on the other hand, Luisa, you have pointed this paradigm in your presentation, and thank you for that. It was very inspiring for me. And also the second issue is the cybersecurity, which must not be neglected in this term. So I think we need to change the paradigm of education, how to educate the new technology in parallel with the threats of various kinds as it could create. In order not to accept it less critical. This is important for me. Thank you.
May I say something?
Yeah.
Thank you for your, okay, in Portuguese or in English? I don't know.
In English, better English.
To answer.
Well, I can read Portuguese, but with
Okay.
talking and understanding directly, I still have problems.
Okay, thank you for your comment. I think it applies to all these types of data. And now with geographic information systems and satellite imagery, you can easily get some software and produce some maps and outputs. And it is very dangerous when they are taken to take decisions, important decisions, because they need to be validated. You can get all types of outputs, but you need to make sure that they are correct. And so this is a very important topic. It's easy to get information, but the question is to get accurate information.
I thank you. Sorry.
No, just one thing about the positioning with smartphones. So we have a project running here, which is to position forest fires with an application in smartphones, and we made already some tests. Just like using a smartphone in the way everyone uses without any special software and with just the app that was developed. And what we found is that the accuracy depends a lot on the phone itself and on the environment. So we got between centimeters of accuracy in positioning of the phones between kilometers, let's say. So it's still, so we need to validate the data. That's an important issue.
Yes,
not just rely on anything that you receive, yes.
Yeah, but I was thinking about using smartphones to validating the data. Because we were talking about acquiring data from the space, and very accurate positioning, and well, the time measurement in nanoseconds. It's comparable to the latency of the switches. In our network, just to prevent for shortcuts. I mean the nanoseconds length, But from other point of view, if you are somewhere in a certain location, we can also, using the smartphones, you can also they could also be used for validation the space imagery processing as well. Okay. Especially. I know. I took this example from fire prevention because it is a problem in Portugal. It is a problem in Spain, and there is the crescent from Europe, from Portugal up to Finland. When I researched this last year, that the probability of fire is growing to more than 2% per year. In Portugal, Spain, in this crescent up to Baltic republics up to Finland. So the application of this for fire prevention could be very important. But well, many open issues. But anyway, we need to educate from the grammar school. That you can use your smartphone, but be aware that it's not true what you see. It could be fake. This is it. Thank you.
Yeah, just to comment what you said. I fully agree with your comments, which are quite pertinent. And in addition to this, there are to the processing issues. There are also things related with the reference systems and etc. that people have to know how to deal in order not to get garbage out of the out of their coordinates.
All true, garbage in, garbage out.
Yes, it is. But in fact, I have to say that this sometimes also happen with the classical geodetic receivers, where some people which do not have the necessary preparation think that it's just to press a button and then to process with some commercial software, and that's it. And then you get quite wrong things, especially concerning the heights, because you have to deal with the geoid information, and people are not aware of that, and this type of things. And so I also agree with Cidalia when she says that data needs to be validated. And in fact, people are given this smartphone, which is becoming a more and more powerful tool to get information. So they need really to be educated. You are completely right. So that they can take part, that they can profit from it.
Yes, so I was thinking in this perspective that the future courses within our initiative, Go to Space Hubs, we can put more time for data validation or other threats. Yeah, I mean spoofing and other techniques which could be used to interfere with the service provision. Yeah. Because how to prevent, how to validate, and how to prevent getting the fake data for further processing. I think we could consider such an issue in the further activities. Thank you.
Okay, I would like to thank you, everyone, to our speakers. Was a great afternoon. Also to thank Jaroslaw to join us all day. Our partner here in Go to Space project, and our team, Carla, Carlos, and Francisca, also went here every day, and of course the participants. We also have here some companies from Go to Space incubation program. I also want to thank you, everyone, and to remember, if you want to contact our speakers, please let us know about it. So I think we can finish if there is no more questions. So thank you, everyone. Obrigada. E vemo-nos em breve. Obrigada.
Luísa, professora Cidália e Joana Laves, obrigado por terem estado aqui connosco e agradecer mais uma vez a vossa presença.
Obrigada pelo convite.
Obrigada pelo convite também.
Depois entramos em contacto também para falar melhor. Obrigada.
Obrigado.